elucidate their photocatalytic mechanism under different light sources. So, how did we do it? We started with bismuth nitrates, sodium phosphate, and bismuth oxybromide, ultrasonicated and autoclaved to obtain that. Then we dry it and add some silver nitride to add a silver nanoparticles on those. And we have three different silver bonds and a sample without any silver in it as a control sample. The XRD data, so X-ray diffraction, show rather complicated spectra. You can see the individual components on the bottom, and you can see that when you combine those spectra together, you can put those spectra of ABPF 1 to 5 very well. So effectively, we are not having a phase change, we have a coexistence of these phases, which is also confirmed by the XPS spectra, where you can have the bonding states of each atom individually, and you can see, for example, for bismuth that we have 2 clear peaks for phosphorus, and we have 2. For oxygen, we have again 2 peaks. However, in this case, the surface and the lattice oxygens have a different energy. It gets a little bit more difficult for silver and iron, as you can see on the bottom of this slide. Where we can have SEM lithographs show that we have composites of different materials discernible. And here you can also see different components, and you can see the circles as the SEAD, so for this composite. So most of the circles, but because we are looking at the magnification, you can see individual dots or individual diffraction planes, which is tricky to that. So, how does that material perform photocatalytically? You can see here under UV light, you can degrade this norfloxacin antibiotic with this ideal composite ABPF3 within about 30 minutes. The BPF, so without any silver, is a little bit inferior to that, and then when we have the individual components, you can see that performance is much less efficient. When you do a kinetic plot, you can see all of that follows nice power law functions. Now the interesting question is, okay, degrading something with UV light is nice and interesting. However, degrading something with sunlight is of course much more environmentally favorable, because we are taking care of that thing using the normal sunlight, and therefore don't require an additional power source. And you can see with visible light, the degradation takes about twice as long, but it still works. The most notable difference is that bismuth phosphate is basically inefficient under visible light. What was also done is to test that under near infrared light, NIR. You can see that also this AEPF3 composite does pretty well, although not nearly as good as under visible and UV light. So, How does it degrade? Well, up here, we start having, we start with this norfloxacin molecule, and then we have the radicals attacking it and cutting it down into smaller and smaller units until effectively we have water, ammonia, and carbon dioxide remaining. So, how do we understand this process? Well, you can see here the infrared UV with UVDR spectra that in the UV range, the materials absorb the light quite well. But in the visible light range, which is around here, 400 to 800 nanometers, the normal single components don't absorb light very well, but materials, they absorb light very well, which explains why they're working so well here. Based on the Kobelka-Munk plots, we can calculate gaps to be quite different, and you can see the same thing for the MOT Schottky plots when we plot it versus a neutral hydrogen electrode. Then we have the PL spectra, which means we can really see how that works, and we have the Nyquist plots and the photo current response for that. So, how does it work on a mechanistic point? For that, we did two kinds of experiments. The first thing is we added several quenchers, and you can see under visible and under visible light the degradation efficiency is getting lower when you add the quenchers, and that gives us an idea about the involved species. And lastly, we have the ESR spectra, which show that when we have which radicals are present. In this case, it's mostly the O2 minus radical and the OH radical, and under UV light we simply produce more of those. And you can also see that when we for the pure binary composite and the composite without silver, the amount of radicals produced is significantly smaller. So let's compare the performances under natural sunlight. And you can see this composite is best, and the total organic carbide good was in the experimental time, which is 1 hour. So it's not that we only degrade the first step, we go down the degradation pathway. So how can we understand this? Z junction
and we boosted those via silver. The amount of radicals produced is significantly smaller. So let's compare the performances under natural sunlight. And you can see this composite is best, and the total organic carbon removal under solar light is still quite good within the experimental time, which is 1 hour. So it's not that we only degrade down the degradation pathway. So how can we understand this? When we have a binary catalyst, we have such a Z junction. When we have the ternary catalyst with the silver in it, then we have such a binary Z junction under UV light, which produces O2 minus radicals predominantly, and under visible light, the O2 minus and OH radicals dominate as well. So this is the first part, and now let's go to some very recent work, only published 2 months ago, on the construction of a new type of Z scheme using carbon nitride, bismuth titanate, and bismuth oxyiodide heterojunctions for visible and solar powered degradation of antibiotics and hydrogen production. And we boosted those via iodide and bismuth redox mediators. So you can see the synthesis scheme here. So we simply produce a carbon nitride by urea pyrolysis, and we make the bismuth titanate by hydrothermal treatment. Then we produce the bismuth, we use this bismuth nitrate and potassium iodide to hydrothermally produce bismuth oxyiodide, but not the normal BiOI, but one with slightly different stoichiometric ratios. Those are then combined in another hydrothermal treatment step. You can see from the XRD data that we have rather 2 bismuth components, and when we are looking at these combined spectra, we can find all the scattering peaks again. So that means, just like in the previous example, we don't have a clear sign of changing the phase structure with our treatment. Then the XPS data show the good coupling. For example, here in case of the nitrogen, we have the C and C bonds, we have the NC3 bonds, and we have the C and H bonds in the XPS spectrum. Mapping, which means we can see in which part of the picture, which is shown in the subfigure D, we have which kind of molecules, which kind of atoms. And you can see here, for example, in subfigure G, that the titanium is only in these particles, but not in those particles up in the corner, for example, while the iodide is in different particles. So that shows clearly that we have 2 different materials. By TEM, we can really see the individual lattice fringes and in the high resolution picture, and we can see how small the individual particles is, which is important because those are effectively surface reactions, so we need a high surface area to make them work. The optical properties are very much similar to what I explained before. So we have a good absorption of our composite in the visible light range, while the individual components, except for the bismuth oxyiodide, do not absorb much light in the visible range. We have the Kupelka-Munk plots give us the optical band gap. The Mott-Schottky plots show us that band gap again. We have the Nyquist plots to show how well the electrochemical performance is, and you can see the current density when you switch the light on and off changes very fast, and the photoluminescent spectra are also very clear. So the photocatalytic properties in this case are split in two parts. The first thing is we are degrading this antibiotic, which of course in the nature would do lots of damage because antibiotics are supposed to be stable in nature for a long time. So you can see here the antibiotic degradation reaches 100%, almost or something like 90-something% within 90 minutes with the CTB30 composite, which turned out to be the best one. However, we could also measure the amount of hydrogen evolution that we found when we so we have a hydrogen evolution that is quite significant for that, and the hydrogen evolution is really very high, and we calculated that we have a apparent quantum efficiency of up to about 28% with that, which is one of the best values that we found in literature. And what we can also say is the degradation boosts the hydrogen evolution. That means, and I'm jumping one slide forward, I'm jumping a little bit forward, when we don't have a pollutant in our system, then the hydrogen evolution is much lower, so almost factor 2.5 lower than if we have a pollutant in there. So how can we explain that? Effectively, you can imagine this, that the pollutant requires oxygen in order to be degraded. Now, when we produce radicals, those radicals contain oxygen and simply are protons. So those oxygen-containing radicals and the non-oxygen containing radicals, if you give them a chance, they will recombine, and then you have water. And that, of course, makes the hydrogen production inefficient. Now, if you have a sacrificial agent in your system, that means you have something which absorbs the oxygen, in this case, because the oxygen likes to react with the organic molecule, you can take the oxygen out of the equation, and that means the hydrogen radicals, so the protons, the hydrogen radicals, they have a larger chance of recombining and then evolve as hydrogen. So for that reason, actually we can say that we are using the pollutants as a sacrificial agent to boost the hydrogen production and therefore make them useful for further purposes. Here we are producing hydrogen here, we're producing the OH radicals down here, and because those go to degrading our pollutants, we have not nearly as much recombination with the hydrogen radicals, so that we can, so that they are safely that they cannot recombine so much, and so they boost the oxygen production. So let's look at the degradation scheme. We have our antibiotic here, and through this rather complex degradation scheme, you see every step requires some oxidation, requires some extra oxygen, and then we are taking it apart into smaller molecules, water, carbon dioxide, and ammonia. And for this molecule, we have the same kind of behavior. So, next question, can we recycle that material? And the answer is yes. So the hydrogen production decreases a little bit, the OFL degradation decreases also a little bit, but not very much.
Hello, Professor Florence Stradley, are you online? Yeah, he's online.
Yes, I'm here.
Yeah, this is presentation.
Well,
So
I can hear you very
shortly.
faintly only.
Okay, so if you have any question, please you can indicate by raising up your hand. While we also invite Stradler to make few comments because it's the video that has just presented. Just a moment, we'll get back to you.
Yeah, please feel free to ask questions.
Okay, so any question? Why make a few comments on the presentation? Question from the audience? Okay, no, so, Australia, can you just make brief comments?
Sorry, I cannot understand you at all. The sound arrives in such a bad quality, I cannot understand anything.
Yeah, we are listening to the video and we're asking for questions.
So,
either from online or okay. Jonathan has a comment for you in the question section.
yes. So I would have to look it up exactly in the.
Let me read it out for you.
So the question is, what flux of photon were you using in your sunlight, UV, and visible light experiments? So for the visible light and UV experiments, we have special lamps. So these are about 500 watts each. For the sunlight, I don't know exactly which flux we had. So it's a normal sunny day flux. Okay. Any other question? So maybe one comment on concerning solar light experiments. One of the big problems about conducting those experiments is that, of course, the sun travels across the sky. And you always need to be prepared that you have clouds blocking your way. So you need to choose the right kind of day and you need to choose the right kind of time and best run all experiments in parallel so that you can get comparable results. And for that reason, we prefer to do our experiments really in our photocatalytic reactor in the lab, because there we have an artificial light source which is very similar to sunlight, but we can very much control it. We can control the conditions, and so we will not have to repeat our experiments, for example, because there's just a cloud coming by or because one tree nearby starts casting shadows. So for that reason, we prefer doing that in the lab. Of course, later for the application, you want to run it with solar light, but for really measuring the performance of different materials and make it comparable over a long period of time, you cannot just rely on the sunlight so easily.
Hello, Bron. I'm not. Have you responded to your comments and questions?
Yes, I responded to the question of what kind of flux we use, and I made a comment about why we use artificial light, but it's not natural sunlight all the time. And it's simply about being able to control the conditions.
Okay, in that case, will it be the same when you use artificial light to when you have the light itself, assuming we come into the real life?
Mm-hmm. Well, the nanoparticles have a certain light absorption characteristic, which is specific for each wavelength. So if you have a wavelength composition of your artificial light, which is comparable to sunlight, then basically it scales only with light intensity. If you use an artificial UV light, for example, then of course the whole situation changes. So for that reason, we have an artificial, we have a xenon light, which is very close to a natural sunlight. And that one works quite well to simulate the effect of sun. Of course, when you use a different light, if you use a different type of light, or also if you have a certain pollution in the atmosphere, which, for example, sand, makes the light appear more red than it is. So that changes the spectral composition, and that's why it will have an effect on the degradation performance. It will work, but it will work in a with different quality if you change the intensity and if you change the spectral composition.
Recording in progress.
Okay, that's fine. Thank you, Strala, and
okay.
We hope to continue with you. And
yes, thank you.
As Dr. Kavi is preparing for his presentation, I would like to let us know that Dr. Kavi is a material scientist currently working as a senior researcher at University of South Africa under UNESCO Africa Chair in Nanosciences and Nanotechnology category. His contribution in the field of functional materials for energy, biocatalysis, and supercapacitor applications have generated new knowledge and delivered 185 peer-reviewed publications and 40 oral and invited presentations at various international conferences. His research excellence is evident through a strong publication record. He has a H index of 55 and more than 8,200 citations. In addition, Clarivate Web of Science identified him for the highly cited Researchers 2020 list. His research is focused on the design and development of advanced materials for low carbon emission technologies, which plays a key role to mitigate climate change. His research activities include surface science of catalysis, electrocatalysis, photocatalysis, and hierarchical nanostructures for tissue engineering and biointerfaces. So let's welcome Dr. Kavi to make his presentation.
Okay, Kavi, you have 30 minutes for this presentation. Can you please take the stage?
Okay. So good morning to everyone to be here. So thank you for giving me the opportunity for the 4th African Conference workshop on the application. Yes, Prof. Can you hear me? Hello,
Kavi,
Prof.
we cannot hear you.
Can you hear me? Yes. Can you hear me? So I have muted, I have on. Can you hear me, Prof?
Kavi, can you go on? We are not hearing you.
No, I have started, Prof. Hello.
Somebody says no, I don't.
Recording in progress.
Okay, Prof. I will try one more time.
Yeah, we can hear you now.
Okay, right, Prof. Prof, can you hear me? Can you see my slides, Prof? Can you hear me? Please confirm.
Yeah, we can hear you. We can hear you.
Okay, thank you very much, Prof. Okay, good morning to everyone to be here on the 4th African Conference Workshop on Applications of the Nanotechnology, so University of Nigeria. So I would like to thank to Professor Ezoma to give me the opportunity today to present of my work is based on the photo fabrication of nickel oxide thin film as a electrochromic layer for smart window application. So my name is Kaviyasu Kasinathan as a senior researcher from University of South Africa. I think, Prof, is an internet problem, but I will try.
Yeah, we are hearing you.
The outline of my the outline of my presentations today. I'm going to introduction and overview. So why nickel oxide is an excellent candidate for electrochromic materials. Some notes of the history and the yearly applications. Recent work on electrochromic oxide thin film, optical and electronic effects, and then some of the result and discussion to discuss synthesis and characterization, and finally concluding remarks. From the introductions of the overview, as you know, in the recent progress made into the fabrications of the rigid and the flexible devices with the nickel oxide thin films is a grounded of the chemical based nodes, which is a versatile properties of the film can be tailored to be matched the targeted applications. So in order to understand the schematic overview of the topic covered in the review, nickel oxide, the material properties, growth methods, and application in devices. So in order to understand the growth method, it's based on the ALD and then CVD and the solution processes. By the temperature, by the properties, antiferromagnetic and the temperature resistivity and then P-type materials. The based on the application wise, it's a LED and then photovoltaics, resistive switchings and the transistors, PN junctions and sensors applications. So the best examples, which is the from the mock-up and the electrochromic, so the virtual binds and the aircraft windows. That is the typical examples based on the smart window applications. Why the nickel oxide is an excellent candidate for the electrochromic materials? In the recent years, nickel oxide nanoparticles have drawn a great interest because of its unique properties. It's belonging to the wide band gap, which is 3.624 eV, which is the P-type semiconductor and is chemically stable with high electro-optical efficiencies, which is it should be the reversible. The optical property should be the reversible from the original shade should be recoverable of the polarity of the voltage is changed. By the way, from that the particular the schematic diagram, it's divided into the three different segments from the anodic oxides and the cathodic oxides. As you know, the anodic oxides of the category nickel to SNO2, indium oxides, and the tantalum. The performance is based on that coloration efficiencies, switching speeds, cylindrical durability, and the transmit mediums. The other examples of the cathodic materials is the tungsten oxide, molybdenum, titanium, and the niobium oxides. Generally, the based on the applications, there was a variety of applications based on the electrochromic materials, which is the best option is the smart windows. Why these smart windows? These properties have an electrochemical materials of considerable interest for optical devices of the several different types, such as element for the information displays like LED boards, light shutters, smart windows, and the variable reflectant mirrors and variable emittance thermal reactors. This is where the electrochromism in the which is based to understand the transition metal oxides. Some other notes of the history and the earlier applications. As we know, as a physicist or a material science, as we know the conducting electrodes and what is that electrochromic or what is the electrolyte, as we know. So in that understanding the particular graph, the particular figure, the cross sections of an electrochemical panel changing from transparent to opaque. A voltage is applied across to the conduction electrodes, and in now ion flows from the ion storage layers. So though the electrolyte, it is called the electrochromic layers. So in the particular graph, just how to develop, how to make the thin film substrates, how to make the preparations of the samples. As we know early, this is the basic experiments, and then the glass I2O, and then coated some of the polymers like a PET or that polycarbonate, rest of things, and then electrolyte layers, and then conductor layers. So that is the typically experimental preparation sample procedures. But the device oriented, and then the two set of the transparent conductors, which is the transparent electric conductors both sides, and then we are using the nickel oxide for the electrochromic layer one side, another side for the anodic materials like nickel oxide is the tungsten materials. So the principal designs is the foil based the electrochromic device. The particular arrows or the ions indicate is a ion transport when a voltage is applied between the two trans segment or electrical conductors. The entire foil can be used as a glass lamination as indicated is the left hand panel. And in the particular slides, the recent work on the electrochromic oxide thin films. So we have based on the different set of materials related to the metal oxide thin films, which is the cobalt oxide, and then the cobalt oxide, and then indium dioxide, molybdenum dioxide, tungstens, vanadiums. There is a lot of oxides like even the magnesium oxide, niobium, rhodium oxides, which is the reaction changes is a different reaction mechanisms, and then color changes with this gradually from one color to another color. So which is that is green to brown, and the color pale grounds and different colors. From the periodic tables, the periodic systems is the chromatomic oxide tables, the periodic systems of the element from the expect from the lanthanide and lanthanide series. Differently shaded boxes indicate the transition with the oxide capable of the giving cathodic and anodic materials. Just simply to choose that the electrochromic materials is just only based on the cathodic and anodic materials. The overall subject is the metal oxides can be the electrochromic devices, implies of the two electrochemical films, and it is clearly advantageous to combine one cathode or the anodic applications. Generally, as we know, those are the cathode applications, tungsten, nickel, titanium, and niobium pentoxides related. The anodic materials is easily to know the nickel and the iron oxides. The another related examples, which is the published report of the based on the band gap energy of comparison the present records. So we have the huge number of techniques like solution growth, thermal evaporations, and the spray pyrolysis, and DC reactive sputtering techniques, and the electron beam evaporations. So when you're comparing with this type of 5 and 6, 3 to 5 different type of preparation techniques to comparison with the different annealing temperature with compared to the bulk and the nanoparticles, even the thin film and the powder technology. Our main objective is to the transition type. So what are the transition type to identify, which is the direct band gap or the indirect band gap. So and the another principle is we have included is based on the energy band gap, that is called the EV. So in our studies, we reported the electron beam evaporations until at 100 degrees Celsius, direct band gap, that is the 3.58 electron volts. So that is the best way of techniques. Is the easy way to carry out the technique is called the EB techniques. In the another notations in the particular slides talking about the opticals and the electronic effects. So as you know, the schematic band structures of the solid state physics, the schematic band structures of the different type of the electrochromic oxides, as I discussed in our main or postgraduate or master graduate text, which they have explained. So shadowed as the regional slightly fitted state of the E donated. I don't want to be the conduction to valent band, that is the same, the basic theory from the solid state physics. Again, I want to bring to the attention of the table column of the chromic oxides, which is the colorations of the anode and cathode. The period table indicates the metal capable of the forming oxides of these two categories. I want to repeat again, the two categories is based on the pointed out of that is a cathode and the anodic oxides. But in the particular slides, talking about the vanadium or intermediates. Why intermediate means WO3 is a cathodic oxides. The pure oxides have unoccupied states, which is the 2Ag. The 2Ag states are intentions of ions and electrons may fill these states to the top of the band. So which is the cathodic oxide is a WO3. It's an unfilled or ions is still completing. So that the material exhibits of the gap is the Eg2 G, it is a anodic oxide, which is called the nickel oxides. So which is the almost that the 2G state and then 2O states are almost completed and 2G is empty. It is exhibiting. Therefore, the materials can become transparent, assuming that the band gap is large enough. Finally, the right hand part of the figure of the which is indicated of the V2O5 with the both the cathodic and anodic features of the electrochromisms. That is the principally different from the electronic structures, which means is a cathodic WO3 is a cathodic oxides and the nickel oxide is anodic oxides and the vanadium is a intermediate materials. And now so let us talk on another slides. Maybe the internet problem. I can't able to move another I can't able to move another slides. Okay, the another particular stage it's related to the opticals and the electronic structures, which is the below transition temperatures and the above transition temperatures. The below transition temperatures to understand easily how is the difference between the structure is a rutile structures, and then so above transition temperatures related to the monoclinic structures. That the typical examples, which is the thermochromic coatings, which is the visible radiation or near infrared radiations. So that is the typical examples when compared to that transition below or the above. So come to the point. So in our the experimental lab, actually we are the same coating as usually the two form of flexible foils of that. So VO2 nanoparticles or VO2 based multi-layer films. Which one you are going to be preferred? Most of the results and the literature which are related to the vanadium oxide nanoparticles. Just as there have been recent discussion. But for the commercial application, as a smart coating or the energy efficient ventilations, there are still several obstacles and the limiting of the relative capability of the vanadium oxide smart coatings. So we want to make sure. So the VO2 nanoparticles is different from the VO2 based multi-layer films, because what are the priority of the commercial application wise? The phase transition temperature, actually the black, as we know, everyone is a 60 degrees Celsius is too high to be applied for the building ventilation, which is that the critical temperatures around transition temperature or critical temperatures around 40 degrees Celsius it is acceptable, which is 20 degrees Celsius it's more or reduce 20 degrees Celsius to reach the 40 degrees Celsius. So that is acceptable for the home to implement or to fix the for the building purposes. For the conventional VO2 coatings, relative modulation abilities are not efficient through the energy solvings, which is for the solar radiation is almost attribution to the transmittance with the near infrared regions, which only accounts of the 43% of solar energy into the solar spectrums. The luminescence emittance it's nearly the less than 40 or even 30 degree due to the absorptions, which means the luminescent transitions. The desirable rate is the short wavelength range is the both semiconducting or even the metallic states or below room temperature, above room temperature, which should be the lesser than 50% at least for the daily applications. Well, the practical, however, the VO2 is the finally transformations in the vanadium pentoxide phase is the real environmental, which is the most thermodynamically stable phase of the vanadium oxides, but it does not possess the thermochromic properties. So the overall the subject of the commercial application, therefore the environmental stability of the VO2 is a great challenges of practical application as a smart window. And some of the results, the synthesis and characterization studies, the result and discussions. From the excited results of the nickel oxide nanorod, it's annealed at a different temperature, room temperature 250 degree. The red curve it's a 450 degrees Celsius. As you know, the basic parametry, as you know each other, what we are going to be understand what we are calculating from the XRD. But the main core area to talking about with the estimated the brand group of the crystalline size to identify, because when comparing with the room temperature or blue, green and the black, to room temperature to 250 degrees Celsius, we cannot find any signature from the XRD. So that only we want to be understand the crystalline size to estimate of the full width of the maximum in terms of measurements. The inversely proportional to the average crystalline size, that is D, as you know, the everyone is the Scherer formula and Scherer formula by the presence of the cubic to confirm the phase group is confirmed as well as the lattice constants also calculated, that is the 4.1 Armstrongs. Again, the lattice strains also is the broadening of the peak, which is related to the relationship is beta strain and equal to 1/4 epsilon tan theta. So in addition to to understand the estimation of the grain size, microstrain grain or stage value, with the reference of the Williams and Holman plot, proposed the methods, which is the converting size and strain, looking at the peak is around to the function of the 2 theta versus the beta cos tan theta, which is called the Lorentz peaks. As we know, most of them, we are using the same formula to identify the grain size of the microstrains. But in addition of to understand to calculate the density location density, which is calculated the formula T equal to 1/d square line centimeter square. So in our case, the nickel oxide nanorods have been, the particle size is nearly, it's a 58 nanometers. The dislocation density is about 1.1 into 10^15 line per meter square. In addition to the absorption measurements, even you know the UV absorption measurements, everyone we know how to calculate. But in the particular case, the normalized intensity, the x-axis and y-axis, the y-axis, the normalized intensity is less into the visible region. It's less than 300 visible region. It is attained the maximum intensity is less than the near infrared region, above 700 or below 300. So even though thickness is the comparatively higher, because the multiple layer coatings is higher, the higher value of the transparency may be because it is the smooth surfaces. So particularly in the UV region, the sudden fall, for example, the red one, the sudden fall in the transmission absorbed into the tidal compounds. The black one is a room temperature, and the green curve is related to 50 degrees Celsius, and the red curve, the C1 is the 450 degrees Celsius. So that one is the suddenly fall in the transmittance. The overall subject of the graph is the absorption coefficients of the nickel oxide is actually the formula as alpha equal to 4 pi k divided by lambda. We know. So why the transition is allowed to direct or direct forbidden, indirect or indirect forbidden. Again, the tau flat to calculate of the energy band gap calculations. The energy band gap, the main important thing, usually the plot is alpha h mu whole square and h mu. As you know, the nature of the optical band gap calculations of the particular crystal or particular nanoparticles. But in the particular case, the band gap of the crystal deducted from the explorations of the linear curve. So compared to the black and compared to the 250 degrees Celsius, and then see each two, and the red one is 450 degrees Celsius. The overall subject is the line interpretations at the x-axis given that it's a direct allowed band gap, which means the direct band allowed is nearly 3.41 electron volt for the optimized room temperature. That is the 250 degrees Celsius was optimized. From the FTR sections to confirm the functional group, because these are the XRD, UV, FTR, these are all the primary investigations based on our tidal compounds. So in this case, from the FTR spectrum of the nickel oxide is the concentrations, which is annealed at 450 degrees Celsius, the same thing, the black, blue, and red. So just want to bring what we are understanding from the FTR spectrum, just to understand that in plane or out plane bending or in plane bending. In the particular graph we investigated, the out plane bending is nearly 280 degrees centimeter inverse, and the in plane bending is nearly 750. From the other the observations, band is centered at nearly O bond C double bond O, which is the symmetric stretching, or the symmetric or asymmetric stretching vibrations, which is the O bond C double bond O or C bond O. So it is related to the asymmetric matrices, and then the water is related to the OH bending vibrations is due to the, as you know, the water molecules which is observed with the nanorod at the ambient room temperatures. And then from the TG and the DTA graph, from what we understand from the TG and the DTA, it's related to the same temperature. The endothermic peak is centered at nearly 120, and the TGA, the TGA curve is the red one. The red one is gradually the weight loss, the mole or weight loss, it's nearly 30.45 degrees Celsius. It's gradually increased to 30 to 160 degrees Celsius. But from the XRD, we want to understand the blue curve is endothermic curve, and then the green one, the green curve is exothermic reactions. The endothermic curve which is centered at the 120 degrees Celsius, the blue curve 120 degrees Celsius, which can be described the following equations, which is the following equation, the temperature is 80 to 160 degrees Celsius. And now the coordinated water is the NOH is nearly 28.96% of the initial compounds or initial compounds of the experiments. In addition to the green peak, which is the exothermic peak or exothermic reactions, as related to the DTA measurements. The DTA plotted of the center that's nearly 2 to 327 degrees Celsius. This is also the represents of the same equation, which is the temperature is nearly 261 to 394 degrees Celsius. The overall the observed weight is nearly 42.2% of theoretical is 41.6, which is the acetone gas and the carbonates. And the AFM images, as we know, the AFM of the nickel oxide, the 2D images, from the 2D images and the 3D images, the depth profile signature graph, it predicts the general assumptions is the morphology pattern of the AFM. The data observed is the reliable of the grain of the higher size due to the tip elevation at the crafts. So which mode you are going to be investigate, or the technicians, or how to investigate the samples, which means the smaller grain size of the AFM analysis yields higher, always the higher values, because whereas the bigger grains or brown grain boundaries in the AFM and the XRD coincidence also. Moreover, the conductive coatings made over the surface priorities, because maybe we are prepared the single oxide nanoparticles or vanadium oxide multi-layer thin films, we don't know. So the overall coating made over the surface priority of the measurements, which is using the sol gel techniques, also altered the grain size effects. In addition to the temperature resistivity and the reactive resistance, how to understand the resistivity versus the temperatures? The main theme of the understanding the resistivity versus temperature plots, which is just to calculate the activation energy. The role of the activation energy using the following equations: rho equal to rho naught exponentials of the EA divided by 2 kT. I don't argue that abbreviation, but logarithmically scaled resistivity against the reciprocal absolute temperature, which is estimated the activation energy values. Okay, I can move to my slides. I will try. Okay, the p-type conductivities. The p-type conductivities and nickel oxides was confirmed by the Hall effect measurements. In addition to understand the resistivity method, the Hall effect measurements are also important carried with the Van Riepel methods. So the carrier concentrations of the crystals, which is the 0.1 into 10 power 24 meter cube, that means it's high electrical conductions. The carrier mobility, it's a very low order to the 10 power minus 5 meter square versus hence the electrical conductivity of the crystal is not bad, that is the moderate. So the another parameter also calculated from that resistivity versus temperature, that is called the TCR, is the temperature coefficients of the resistance. It's using the relations, the formula is the TCR, it's a R1 minus R2 divided by RT, it's a T1 minus 2, which is the R1, R2 as the resistance temperatures, and then the T1, and then T1 and the T2, it's similarly the obtained temperature coefficients of the resistance values, which is order of 10 power minus 3 kilogram per inverse, which means the negative values. The negative value means, which means the negative values of the transition coefficients of the resistance, the semiconducting nature of the prepared samples. From the field emission scanning electron microscope, that is the FECM images, to understand there is the 8 different set of figure from figure A to H, the different morphology pattern from the FECM images and different crystalline sizes, and then the orientation is different from the different magnification from 50 nanometer to up to 5 nanometers. So the overall the subject, what to understand from the overall the subject, which is the mean particle size determined by the same. The overall, the average particle size or the mean particle size determined by the FECM, it's very close to the average particle size. By calculated by the from the XRD is a Debye error formula from the XRD pattern. The again same pattern to calculate the HRI resolution scanning electron microscope images from the nickel oxide nanorods. The shape of the from the figure A to D and the E to F, the pattern of the morphology of HRTM images the various or elliptical or hexagonals on the polyhedral that up to 30 nanometer from all temperature, and then the IV characterizations up to 450 degrees Celsius. The electrical resistivity is nickel oxide core shell structures as a function of temperatures of a typical metallic behavior observed in all cases, which means the resistivity decreasing with increasing reduction temperatures. So this is due to the decreasing volume fractions of the minor phases of the nickel bond oxygen in the systems. The resistivity of the nickel oxide is at 450 degrees Celsius which is that green intercept line was the bulk, maybe the order of the magnitudes. The high value of the resistivity is due to the grain boundary scattering from the nickel nanorod, as well as due to the presence of the same quantities of the nickel oxide. And the last characterizations of the X-ray photoelectron spectroscopies. The XPS, the X-ray photoelectron spectroscopy image of nickel oxides from the particular tabular column, it's demonstrated the different type of parameters we have investigated, and different set of materials like nickel metal and the nickel oxide and the nickel Ni2O3s and another nickel related to different techniques. In my case, my research is based on nickel oxide nanoride, which is confirmed with the oxygen O1 spectrums, which the O1 spectrums is of the synthesis from the graph. The sample is annealed at nearly 450 degrees Celsius. The deconvolved by the Gaussian curve corresponding to the nickel oxides. So the high intensity peak showing the binding energy is the O1 state is a 532.30 electron volt, indicate is a nickel oxide is consistent with the results of the XRD and related to morphology images. And then I want to try to move another slide. Okay, the conclusions. Okay, the conclusions, and then sorry, I can't able to. Okay, the conclusions and practices. The electrochromic properties of a number of transition metal oxides have been known for the decades, and their application devices has been attempted for many years. In the many research groups across the world, across the continents, they are working with the transition metal oxides. Particularly the most attractive thermochromatic technology. The best examples, the intermediate materials. I'm not talking about here, it's based on the future. It's not the anodic material for cathodic material. The most of the anodic cathodic material, it's related to the solid state fuel cells, and the batteries, it's related to the energy applications. But in the particular case of the attractive, the electrochromatic materials, the VO2 is the best materials for the coating applications have been gained greatest attention by researchers across the world, and many efforts have been made to promote the real commercializations. Nevertheless, research and development have progressed at a steady pace on oxide-based electrochromic technology may finally, in the near future, that is 2025, be ready to make market introduction into the massive scale for the building construction purposes, particularly household equipments and the building construction purposes. However, more efforts are still needed to make this technology into bring our daily life activities. So in the acknowledgements, I wish to thank to all co-authors and my co-authors for kind support and the encouragement to do this work. So I thank to Chairman Professor Malik Maza of the UNESCO University of Africa Chair in Nanoscience and Nanotechnology for funding, and then Administration Secretary of the Cheryl Erasmus. So finally, thank to our valued colleagues, those who are from internationally, collaborators and friends and colleagues. I would like to thank to the University of South Africa, and then the National Research Foundation, which is Aitambalaks of the Accelerator-Based Science, is located in Cape Town, South Africa. So finally, I wish to express my gratitude to the Chief Patrons of the University of Nigeria and their college executives, deans, the organizing committee members, today the moderator of the Professor Rose, Soji, and Professor EP Yugu. Okay. Thank you.
Okay, can you give him a round of applause, please? Kevin, we thank you for this presentation.
Yes, Prof.
So we just have, if anybody has a question, please can you indicate? Otherwise, we'll move to the next presenter. Any question from the audience? Kevin, there's no question, so we quickly move to Rao. Rao, can you please come on? Thank you so much, Kevin. You have to see very soon.
Come in, Prof.
Yeah, we'll see very soon.
Thank you so much, Prof.
Okay.
Bye.
Yeah, Rao, can you unmute yourself and then go on?
Hello. Hello, can you hear me?
Yes, we can hear you.
Okay. Can you see my slides?
Yes, we can see very clearly.
Okay. Thank you very much, and good morning to all. I'm going to. Yes, please. Hello.
Yeah, we hear you.
Okay. Shall I go on?
Yeah, you can go on. I'm hearing you. We're hearing you.
Okay. Okay. Thank you. So I'm going to talk on molecular dynamics simulations and transport pathway calculations for energy storage materials. First of all, I would like to thank the organizers for inviting me to give a talk at this place, particularly for Professor Azima, who's in touch with us for the last few years, and we are working on different areas. Till now, you must have heard various talks using a lot of equipment and trying to identify the applications and try to understand the properties of materials. But here I am going to introduce something which is more economical, and you can do better things, and you can bring the results on for with the experimental results. Before I go into details about my presentation, I would like to introduce my organization, which is called CIMET. It's a Center for Materials for Electronics Technology under the Ministry of Electronics and Information Technology, which is at New Delhi, and we are at Pune, which is headquarters, and we have three different centers, which is one is at Hyderabad and the other one is at Thrissur, which is in Kerala, which is both are almost the southern part of India. And we are at the middle part of India, and all these three centers we have different core areas of research, particularly for mostly for government organizations we are working. And if some of you are interested, you are always welcome to join with us and do some research here at our institutes. These are the few pictures I picked up when I visited Nigeria in 2014, when the first conference happened there. So I could see and still remember the days where I spent there, more about 8 to 9 days. And I should say thanks to Professor Azima again for inviting me there, and we could spend a good time, and we could share a lot of information there over. Coming back to my presentation, why should we do simulations? The simulations are more cost effective. Please bear with me initially. I will try to give an introduction so that everybody will understand more about, and then I move to results. So you need these simulations are cost effective, and you don't need really much chemicals, and you don't need expensive equipment, and you don't need to waste any chemicals in this one. And time. You can run many computers, many compounds in parallel. That save a lot of time for you, and space. You don't need to have really big spaces, and you can run on computers and servers. And the results, you can come near to the experimental results. And once you're convinced, then you can go and do experiments. These simulations, based on the time scale and the size of the particles, they are the system that you can divide into ab initio calculations. You can do in angstrom level up to nano level, and then you can go to semi-empirical methods you can have, and then if you have more number of atoms, you can go to atomistic level simulations, and then further
you can move to the mesoscale method, and then if you have even bigger for engineering purposes, you can go to the continuum method. So this is the range of the simulations one can work, and you need of course, when you go for the continuum model and all, you need a high power computational. I try to give pros and cons of different levels of these simulations. For example, you take electronic scale, which is called ab initio calculations. And these calculations you need to solve using Schrodinger equations, and you can solve only a particular number of atoms. You can't really do too many atoms, maybe maximum about 100 atoms that you can work on ab initio calculation. But the results are very near to the experimental results, and you can reproduce the results which you can do experimentally, are even more finer than what you do in experiments. You don't have any errors here or human errors like in these simulations. And because it's more and classical atomistic simulations I'm talking. So this, if you have more number of atoms, for example, up to 10 power 6 number of atoms, and you want to run this for long scale, like 1 microsecond, you can use these simulations. These simulations are mainly depends on the solving of Newtonian equations. As I said, you can use so many number of atoms in the simulations, and in the simulations can be either molecular dynamic simulations and can be Monte Carlo simulations. And these molecular dynamic simulations are mostly solving or integration of equations of motion, and try to relate the properties of these materials that we do in these molecular dynamic simulations. And these molecular dynamic simulations, as I said, the solving of the Newtonian equation, you know, the Newtonian equation, the relation between acceleration and force, and this force will be derived from the potential between two atoms, and then you will go for the equation like World algorithm, which I will show later, try to do in time steps of 10 power minus 15 seconds. And this modeling, initially you need a position, momentum, and charge, and the bond information. So what type of bond information you need for this one, and what type of potentials you need for this one. As I said, this is a Newtonian equation, and you can get the acceleration from this equation, and which is directly relating with the potential energy of your material. And this potential energy can be in two forms. One is a bonded, and the other is a non-bonded energy. And this non-bonded energy can be again van der Waals potential or an electrostatic potential. And these van der Waals potentials can be written like this formula, which is Lennard-Jones potential, and for a non-bond pair of atoms. And you can have this is if you consider this A and B, or depending upon the type of atoms which are existing in your system. And the electrostatic interaction, of course, you know very well, this is a Coulombic interaction, which can be written in this form also. And the total non-bonding for energy, or the potential, will be in the form of van der Waals plus electrostatic energy it comes in. And in addition to that one, the bonded atoms that can be different forms of bonded can be bond stretch, and there is a possibility of bond angle, and there is a bend in the bond angle, and there is a rotation in the bond angle. So you need to consider all these parameters when you are simulating a system, particularly when you are simulating a molecular system. So this is how the equation, you can see the bond length potentials, the bond stretch that you can calculate using these relations. And then the bond angle potentials, is there any bend existing in this system? You can calculate using this relation. These are standard relations, but I wanted to show you a recap for you so that you can bring the relation between what I am talking later. And then the next option is you will have a torsion potential. That's the rotation at one particular one particular corner you can have, and about one particular atom you can see in a system. Once we have all these potentials, then we need to define the position of the atom. That's what we use as a Verler algorithm for this one. You can see the expression for Verler algorithm. And once you have this Verler algorithm, you will need to understand how this velocity will be correlated. That is what you can get from this equation. This is called autocorrelation function for getting a velocity of an atom, which is in your system. In addition to the position and velocities, you need to define the boundaries of a system. If it is a crystalline compound, you need to tell what is the position at which an atom is there. If there is a possibility of crossing over the boundary, how should it be, how it is going to affect this, you need to define this, are called boundary conditions. And normally in organic compounds, there is no boundary conditions people use, and there is a possibility of using mixed boundary conditions also, saying that along x-axis and y-axis, this is a periodic boundary condition, and along z-axis, you don't have any periodic boundary condition. It can be infinite. That is also possible in the simulations. This is what I was telling, that if an atom move from one shell to another shell, you can able to calculate how it is moving, and you can define the boundary condition, how this is happening, at what distance it is happening. You can define these parameters in your simulation. This is starting of the simulation. So once you have all these parameters, and then you will see how the potential is varying over the distance. That's, you should not have a cutoff potential at one particular distance. It cannot be a step potential. It has to be as smooth as possible, so that the interaction, because of one atom, will not die at one particular point. It will continue to a certain level, and then slowly it goes down. It's a kind of exponential function, but it is not really exponential function, as a error function actually. And there are different types of molecular dynamic simulations which you want to perform based on the requirements. Is called, for example, a microcanonical ensemble. You will have a constant number of particles, and volume and energy you will be considered in this system. And in the grand canonical ensemble, you will have there you will have a constant number of atoms, volume, and the temperature. And then you will have isothermal system. That you need to have a pressure constant and temperature constant. And the grand canonical system, you will have to have a chemical potential which is constant, and volume and temperature. So you need to choose which is the best suitable for your system, which can define the properties that you are ever looking for. And these are various potentials available in the literature. You can see Mohs potential, Buckingham potential, Lennard-Zun potential, and Bornhagen Mayer potentials, which gives three body interaction also, along with the two body interaction. Once you are done with this, and how to calculate various properties, particularly I'm looking at the energy materials, ionic conductivity is most important for me. So for that, I need to understand what is a correlation function, a pair correlation function, which gives me the distance between two atoms, And the running coordination gives me the coordination between two atoms, and the mean square displacement gives that leads to diffusion coefficient later. You can see the relation between the mean square displacement and diffusion coefficient, and then leading to the ionic conductivity. This is an example. People can do number of expressions. You can come, for example, instead of Nernst-Einstein equation for the ionic conductivity, one can use Green-Kubo equations also. And once we have the systems, we come up with the bond valence approach for further analysis of these materials, particularly for calculation of the transport pathways. This is a simple chemistry which you have a bond valence sum of an atom, which is a cation. It can be expressed as a sum of bond valences because of these anions which are around. In ideal case, this will be equal to 1, but in the practicality, it is not real. It doesn't equal to 1. That's why there will be a bond valence mismatch. You can see the expression here. This bond valence mismatch can be converted into this expression can be turned into energy, and you can make into this energy like this. So once you have this particular energy, and this you can convert by adding the Coulombic interaction, you can make a full potential. And so once you have these potentials, you can use for these same potentials for molecular dynamic simulations also. For example, I'm giving you here lithium, oxygen, lithium, fluorine, vanadium, oxygen. You have a number of these atoms and the pair of interactions and the various constants which are involved in this particular equations. For your reference, you can see this. We have done it. We have tabulated all these number of available atoms in the periodic table, and their interaction with the different atoms, which we already reported in our previous manuscripts. So now starts the results of using all this, but first starting with the bond valence approach. So we wanted to see the transport of these ions, how they are migrating from one position to another position. For example, in this copper iodine situation, we need to compare our initial results with the experimental results. So we have the map, electron density map, which is taken from MEM. Then we try to superimpose our results with the experimental data which is given. So this is how the transport pathway is happening. For you can see how it's correlating our experimental result, our simulation result, the bond valence calculations with the experimental results. You can see which we are reproducing the experimental results. But if you want to do this electron density mapping, you need to really spend a lot of time at synchrotron and neutron centers, but you don't need to do that if you have this bond valence approach, and you can calculate the same, and you can reproduce the same results here also. And another example where this you can see the bond valence calculations, and we are getting energy here using the transport energy, which is the transport energy from one position to another position, and this is based on NMR. You can see how well they are correlating. For example, in this case, from CN3 to CN6, the activation energy, which is calculated by bond valence, is 47 kilojoules per mole, and you can see this is NMR result. And one more advantage of this one is if you do normal impedance analysis, you can't distinguish whether this particular material is a two-dimensional material or a three-dimensional material. But in this case, we can do. This is how you can. This is energy for a 2-dimensional transport, and this is the energy at 3-dimensional transport. On average, you will get a 3-dimensional transport when you do impedance analysis, and also the same happens if you do NMR. You can get this type of activation energy calculations. So you don't need to have NMR. If you do simulations, you can get the data same as which is fairly matching with the experimental results. This is one of the examples which we have done for lithium silicate, which is a glass material. In fact, this amorphous material, and we calculated the activation energies and try to see how the transport is happening in this system when a particular bond valence mismatch is taken over, and then we try to explain the conductivity effect of lithium, sodium, and potassium by replacing in the silicon oxide. And there is another example where scandium vanadium oxide we have taken and try to see how the transport is happening at this particular temperature. You can see 1300 Kelvin, which is about 1000 degrees centigrade. That you need to have really good system to do the transport calculation to measure your ionic conductivity. But in this case, we could do simulations and try to understand how these ions are mobilizing or moving in a system, and then how they are traces. You can see how these ions, some of the ions or the atoms, they will be migrating only at the mean positions. But some of them, they will go through and they will even cross over the one unit cell and move to another unit cell. That's what you can see the traces of some of atoms. They are going throughout the crystal structure, which you cannot see using your laboratory equipments. And another example we studied is barium fluoride when it is a combination with the calcium fluoride. And so what is happening at the interface? You need, if you want to study this type of interface studies, it's really difficult to do in a laboratory. But here you can see how the interface is, the transport of the calcium and bromine is happening at the interface. You can see clearly and understand how the conductivity is changing. The fluorine diffusion is happening at its interface. And if we have a good compound, and if we can replace this calcium with some other atom, you can study them even before you go to the experiment. And once you are confirmed that this is giving a good fluoride and conductivity, then you can do experiments, and you can get your fluoride ion conducting. For example, you can have a battery, fluoride ion conducting battery kind of stuff. You can do whatever you want. Another example which we have taken is LGPS. If you are in a battery community and working on solid electrolytes, particularly, this is one of the highly conducting battery. Solid electrolyte, which is of the 10⁻⁻² Siemens per centimeter at room temperature. And we wanted to see why this is happening, how the conductivity is happening in this particular system. So initially, we see this as a 2-dimensional transport is happening, and then at one particular energy, there is a possibility of 3-dimensional. Initially, it was 1-dimensional, and then it leads to a 2-dimensional transport is happening. This is what the isosurfaces which we could get from the bond valence calculations. And we further try to analyze even deeper and try to see how the transport is happening. So this is the position of lithium ion here, and it moves to the interstitial position and then move to this one. This is how this is a cooperative movement of the ions is taking place, which is the responsibility for the ionic conductivity of this compound. And then we further try to see how the molecular dynamics is happening in this system. if you see, observe closely here, in addition to the migration of the ions, sorry, yeah, in addition to the migration of the ions, there is a rotation which is happening in this system, which is helping for the high ionic conductivity of this compound. So this also you can explain very well in this compound, in these systems, using bond valence approach combined with molecular dynamic simulations. And there is another compound which is well-known compound, lithium iron phosphate, you know, and there is a always a debate whether it's a one-dimensional transport or a two-dimensional transport. And what happens if an anti-site effect is happening? That means in place of lithium, if iron go and sit, what happens? So if in place of an iron, and if a lithium go and sit that, then it leads to a conductivity transport perpendicular, and there is a break at the transport here and leads to a two-dimensional transport. This is very difficult to do in a regular experiments, but you can show this in the simulations using bond valence. So this is how you can see clearly how the traces of the ions are taking place throughout the system. And then, yeah, this is another way of representing how the transport of this anti-site disorder is leading to a two-dimensional transport in addition to the one-dimensional transport which is happening in the system. So like this, you can do a lot of experiment studies using this bond valence approach and molecular dynamic simulations. And then if you want to replace, for example, in place of lithium, if you want, in place of iron, if you want to replace with the sodium, what happens you can study. And in place of lithium, if you partially replace the sodium, what happens you can study. You can do a lot of such studies in this way. And in addition to that one, if you have different combinations of the materials and what is happening at the interface, you can study, and this helps you to understand the capacity fading in battery materials particularly. So this is, you can see a glass material which is interfacing with the crystalline with the LiFePO4 compound along a 010 surface, and you can see how the transport is happening at this phase, and you can understand how long this glass glass electrolyte can sustain against this particular LiFePO4, and how fast you can charge a battery and how fast you can discharge a battery. You can do this kind of studies using this bond valence approach and molecular dynamic simulations. And then another example I'm giving here is this is also another good cathode material, LiFeSO4F, fluoride-based compound, which is a high voltage compound, and we could do the diffusion coefficient can be calculated using both ab initio both molecular dynamic simulations and experiments, and we could show that they're matching on for very well. And there is one more compound, vanadium phosphate compound. This is the last example I'm giving. If you have a space structure, space group like this, and then you can do molecular dynamic simulations and transport pathway calculations and traces of these compounds along different directions, and that's what. And not only that, you can see how the diffusion coefficient is changing along x-axis, along y-axis, and along z-axis in this particular compound. And then you can dope you can create vacancies in the system. For example, here we created a 7% vacancies and try to see how the diffusion coefficient is changing. Now you can see there are two diffusion coefficients, which is leading to two different activation energies, and you will find the activation energy at lower lower temperature, one particular activation energy, and higher temperature, another particular energy, activation energy. This is, you can see, you can explain why such type of phenomena is happening, and you can understand at which temperature we have to operate this particular battery if you are using this particular materials. So bringing to the conclusion, so simulations can help us understand the properties of the materials with the minimum or no chemicals, and the time consumption is very limited. And the molecular dynamics simulation combined with the bond valence calculations can be a very good tool to understand the properties. I did not show you a lot of properties we can calculate, but since I promised that I will talk about the transport pathways, and I just gave a talk about the transport mechanism. So if you are interested, you can contact me, and we can do a lot of work on this one. And thank you very much once again for the organizers for giving me this opportunity. Thank you, sir.
Are we put our hands together to Professor Rao? Thank you, Prof, for your great presentation. So listen to one or two questions. Any question from the house? Okay, we have one question. Prof?
Yes.
What code did you use, and your potentials? Did you actually make the potentials yourself?
No, can you please repeat, Mr. Chair?
And the potentials, did you actually derive the potentials yourself, or do you use that?
Yes. You're asking about the potential.
Yes, the potentials, did you actually derive them yourself, or you use standard potentials?
Okay. For molecular dynamics simulations, we are deriving the potentials for bond valence calculations, which I gave you, we showed you already the parameters which are given, which we are not using a rigid bond valence calculations, but we have a concept of non-rigid bond valence calculations. So we are deriving these potentials from our bond valence calculations and using them for molecular dynamics simulations.
And which code did you use for your molecular dynamics simulation?
Okay, molecular dynamics simulations. Yes, we are using DL Poly. We are using Material Studio. Yeah, these two are the basic ones. And in addition to Material Studio, we apply Gulp, Gaussian. We are doing.
Okay, thank you very much.
Yes.
Okay, thank you. Any other question? Okay, once again, I will put our hands together to Professor Rao. Thank you, Prof.
Thank you, sir.
So you can stop sharing your screen. So let's listen to another presenter. Now we'll listen to Dr. Kingsley Obodo. Dr. Kingsley Obodo is a research fellow in the Department of Physics at the University of South Africa, where he has been a member of the High Performance Computing Group since 2016. His research year fellowship. Kingsley completed his PhD at the University of Victoria, his MSc at the African University of Science and Technology, Abuja, and his undergraduate study at Nnamdi Azikiwe University, Oka. His research interest lies in the following areas: quantum mechanical study of solid-state system, magnetic and thermal properties of materials in nanoscale, defect, surfaces, semiconductors, interface, electronic properties of energy relevance material and catalysis, computational high throughput screening and high performance computing. Kingsley is highly cited author with numerous scientific publications. He's currently a member of the profession. He also contributes to scientific citizenship as a reviewer. He has collaboration activity worldwide. And welcome, Dr. Kingsley Obodo. You're welcome.
Hello. You will really need the mic. Can you hear me? Hello. Hope you can all hear me. Just a quick correction. I'm now in Northwest University and I work for HISA, which is Hydrogen South Africa. So, but it's still okay. I'm still in South Africa. So that's why the t-shirt HISA. So, will I be able to see the presentation? Okay, the topic I gave is, I just made it short here. So I'll be looking at dehydrogenation of liquid hydrogen carrier. So we'll be looking at it from a density functional theory. And the previous presentation was a good preview to what I'll be talking about. So he looked at modeling of materials using molecular dynamics, and he tried to explain it from a pedagogical point of view. So I wouldn't go so much in depth because I don't want to bore everyone with the theory. So I'll try and give a brief highlights and then go deeply into what I studied. So, so this is my center, and I just took this picture and then I put so you know where I am now. Next slide. Okay, our current center where I work, it's sort of a high-level center that tries to focus on developing hydrogen economy in South Africa. So hydrogen economy is quite important because I think South Africa has about 60% of the world deficit of platinum. So beneficiation of platinum is very important. Platinum was previously one of the main material used in auto catalysts and it's quite expensive. So if we talk about going green, it means that as we have now, we might have different kind of cars. So you want, if you want a greener car, you don't. It means that the price of platinum might crash. So we need to use platinum for something else. So we can actually use platinum, which is a very big driver for a lot of catalytic reaction. And then some of you that have money, you buy platinum and then you have platinum rings, but that's not going to drive revenue as much as we want. So we want to use it for other reasons. So which is why our center was established to help in beneficiation of platinum. So that organogram just shows the high level kind of research that is being done by the center in different aspects. So What you cannot see, what will you need to see?
hello. So organogram I showed earlier on just showed the high level of what we do in our center. So the aim of so this shows what we do. So next slide, please. So like I was trying to explain, the need to go green is very important. So this just shows petroleum use and the rest of them, how it's been rising and how we need to introduce different energy sources.
So Nigeria as a country, if I was in Nigeria, maybe I'll be working for a petroleum institute trying to make sure that we can sell more oil. Because South Africa, we don't really have oil there, so we have to work with what we have. So the energy consumption has been rising. You can see like the use of coal, petroleum is increasing, but there is still an opportunity to reduce our reliance on petroleum and coal. And this opportunity is what we are trying to tap in here. Please, the next slide. So what is important is we need to look at innovative ideas towards how to do this. So we look at adoption of renewable energy, generation of renewable energy sources, sustainable technologies, energy storage, and fundamental understanding of processes involved in renewables. So a lot of R&D is essential. So this map also shows the different spaces that is being that people are working on currently. We're playing in this space, hydrogen. It could be a solution for a lot of things. Hydrogen could be a solution for storing energy. Hydrogen is feedstock for a lot of chemical processes. Hydrogen, you can use it actually for heating. You can use it for a lot of things. So this is the space we're playing. We're playing in the space of how to store energy and how to transport energy. So if you look at something like hydrogen, there's lots of ways. I mean, most of you don't know, but technically almost everything you do, you kind of use hydrogen. So there's a lot of compressed cylinders. You compress hydrogen in big cylinders. Now, it has advantages and disadvantages to go that route. One of the advantages of compressing hydrogen is that you can easily transport it, and is what we know. But the disadvantage is because hydrogen is so small, you can't transport a lot. You need to pressurize and pressurize and pressurize. So we can use chemistry, smart chemistry or smart physics, to bond hydrogen to chemicals that can release them when we need them, and then we can have what we call onboard use and onboard release. So which is what the current the later part of the talk will focus on. So I've explained why hydrogen is important. It's applicable in a lot of places, and this is why hydrogen is important. So I won't just continue preaching about hydrogen, even though my center we preach about hydrogen. So like I was explaining, you see, if you have your renewable energy, one route is battery system. Another route is you can get your renewable energy. So we've got solar panels where I work, and then we use our solar panels. We've got electrolyzer. This electrolyzer, we can break water into oxygen and hydrogen, and then we can use the hydrogen for different stuff. So our center was quite useful. We got because of COVID-19. So our waste product is oxygen. And oxygen was key recently when people were getting hospitalized. So what we discard and we save waste became very important, and a lot of people sell oxygen. So if you look at, like I was explaining, one of the more matured system of transporting hydrogen is 2 cylinders. It's very matured, but we're looking at newer ways, which is this method, which is not as matured as compressed cylinders, which is bonding hydrogen to organic chemicals. So I'll focus on that subsequently. Okay, before I go to that slide, I just want to mention, when I say bonding hydrogen, we've got, I assume all of us have a bit of chemistry background or some background. So we understand that there are different chemicals that have hydrogen, like you've got methane, CH4, you've got 4 hydrogen, you use methane, but the problem with methane is a gas. So you have something like cyclohexane, which is, you can also store hydrogen on it. So there are different molecules you can actually store hydrogen. So you can take out the hydrogen that you stored there and later put back the hydrogen again. So that's what we call liquid organic hydrogen carriers. So we've done a couple of work in this space. We keep publishing our book on this space. So I'll be focusing on this particular work that we did. So the concept is there's something called hydrogenation and dehydrogenation. So hydrogenation is you put hydrogen on the molecule, dehydrogenation is you take out the hydrogen. So it's an easy way to carry a lot of hydrogen instead of compressing it and compressing it. So we need to develop catalysts that carry out this kind of reaction. And so this is just a typical system that for the hydrogenation and dehydrogenation reaction. So you can get your hydrogen through an electrolyzer, you hydrogenate, then you can charge your LOHC. So charging here, it's more like hydrogenation. And then you take it to your LOHC storage facility. You can use the LOHC as a fuel. So this concept is actually, we've demonstrated this concept, we use it in the mine. The reason why it's very useful is that the mine uses very big equipment, and these big equipments, we can use our LOHC molecules for this kind of reactions. So it is very good. So next slide, okay, yeah. So I'm using this molecule to lead to the dicyclohexane. And you see, we can store about 6% hydrogen on this material. We have bigger molecules like I think your naphthalene and the rest that store more hydrogen. And in my group, some other people are working dibenzyl toluene for storing hydrogen. So there are lots of molecules that are essential, but this presentation focuses on this. And part of the reason why, so a lot of times when we use a molecule, we have our reasons. Part of the reason why we're looking at methylcyclohexane is because South Africa, we've got winter and summer, so you can get very cold. And we work also with European partners. So when it gets very cold, if you use bigger molecules, then the molecule, it's your rheology, the flow of the molecule would not be proper. So you want your molecule to flow nicely. So we use some, even though it doesn't take as much hydrogen, but we can use it all year round, both in summer season and in winter season. So if this technology was developed particularly for Nigeria, it would be better to use something like a bigger molecule because it's always hot here, so it will work better. So I think I've done a bit of explanation. So I talked about the challenges while we're using methylcyclohexane. So if you look at what happens here is you can take out in your dehydrogenation cycle, you can take out 3 molecules of hydrogen. So in your hydrogenation, you put in 6 molecules of hydrogen. So the essence of this is that if I use this for storing hydrogen, at any point I have 3 molecules of hydrogen, but or 6 molecules of hydrogen. So advantage of using this system again, liquid organic hydrogen carriers, is because of that your system is more stable, so you don't worry about it going on flames. So I'll be introducing new things as we go along. Part of the reason why we use something like this is recently we had a very huge violence in South Africa where people were looting and burning stuff. So they introduced a new legislation that bans in a can because you can use it to set fire. With a molecule like this, you put it won't burn. So it's so even if there's riot and people say, okay, we're using our fuel, you can't burn this molecule, so which is very good. So it's practically very stable. So what we're doing here is, like I explained, platinum is our business. So I introduced layers of platinum on something called magazine. So magazine was discovered in 2011, and the magazine molecules are like clay. So you can use them. There's something called like a core shell. You can use the magazine as the core, while you actually introduce tiny bits of platinum on the surface. The reason why we're doing that is we're reducing the platinum loading. Platinum is quite expensive. Even though we're trying to develop technology to use platinum, we're reducing the amount of platinum because if we don't do it, if we don't know this technology, somebody else will use it, will do it. So this is just the computational details of the calculation I performed. So what we did was we used the code called Material Studio, and then these are not to bore you, but if you're interested, we can go into the details. We calculated things like the reaction energy, the different configurations that are essential. And then from these, we were able to tell whether our system we are studying, whether it's feasible or not feasible. So From our calculated binding energies, as presented on the other side there, we found out that all our platinum binds on this surface, and then they bind visibly. So the essence of it to bind is that if you want to put platinum on something, you need to be sure that it's going to stick. If it doesn't stick, then it's just not going to work as it's not going to work. So which is why we calculated this, and we found out that our platinum, they all visibly bind and then they can stick on the surface. We use sorry, I'm still waiting for it to come up. We use something called the absorption locator to screen for different configurations. So our molecule, when we introduce, after we put our platinum, we need to find out that our molecule too would bind on the surface, because what I'm developing here is a catalyst that uses less platinum, and we use something that is cheap, like titanium carbide is very cheap. So it's like clay, so with smart chemistry, you can make this particle, so it's very, very cheap. So you don't want to use methyl cyclohexane would bind on the surface, or would be what is the favorable configuration. So we use an absorption locator model, and then we determine the minimum energy. And this minimum energy configuration, we will use it for our calculations. Okay, yeah. So we calculated the different absorption energy of our molecule on the surface, and we found out that the binding of this molecule and all of its intermediates are principal on the surface, which is good. Subsequently, we look at different schematics of dehydrogenating methyl cyclohexane, and then we calculated our reaction energy. And so from this schematic, that's the schematic presented here. For the various reaction energies, you will find out that if you just have the magazine, the titanium, the Ti3C2, molecules are negative. And that is a problem because we know that our dehydrogenation reaction is positive, it's a positive reaction for several steps. So it means that the first molecule, just using your plain magazine alone is not feasible for this kind of reaction. So we looked at, but using it as a support, as we can see, is feasible for this reaction. And we evaluated different pathways. So we found the optimal pathway, the abstraction pathway to be 6, 1, 2, 3, 5, 4. So we need to know which hydrogen goes out first or which one doesn't go out. And we need to know if they are all favorable and the energetics. Okay, so we calculated the various energies for the different pathways as presented here. We found out that I explained this already, that exothermic energy is calculated might imply that the molecule will disintegrate. So if you just use Ti3C2, our molecule will disintegrate, and you don't want it. This technology is supposed to be renewable in the sense that even though we are using a petroleum product, we want at the end of the day, when you do a reaction, your molecule is still intact. So we just change from, let's say, methyl cyclohexane to toluene, and then we can still hydrogenate toluene to methyl cyclohexane. So we are not breaking our molecule. We still have we're just loading with hydrogen and unloading with hydrogen. So based on these, we found out that all of these different number of platinum on the methyl cyclohexane, they are endothermic. It means that you need to add energy for this reaction to proceed, which is what we expect based on our experiments and other studies. Hello? Hi.
Share.
So, in conclusion, I've showed you a few things, and then I'll just try and talk about the method. The method we used is density functional theory for the modeling. So we did modeling with density functional theory. We've shown that this method is applicable to study something like LOHC, and LOHC is essential, which is liquid organic hydrogen carrier. It's essential for storing hydrogen. So we kind of developed a novel configuration to reduce platinum loading for this kind of. I think I don't want it to be too technical though, but we obtained improved catalytic activity for our platinum, and then we also found that we can reduce our platinum loading. Remarks. So we have other ongoing projects, such as we are looking at how to develop new low PGM catalysts for hydrogen evolution reaction. We working on oxygen evolution reaction. We're looking at improving the catalysts we have currently. We are looking at other kind of designing and characterization of 2D materials as catalytic as catalysts for different kind of reaction. So if you are interested, yeah, we can actually work on some of these kind of projects together. And lastly, I would like to acknowledge my center, which is High Science Infrastructure and Northwest University for their support, and I would like to thank you all for listening. Yes. We have two questions.
Thank you for your presentation. I have two questions. One, for this kind of work, the dehydrogenation kind of project, can you run the molecular dynamics calculation for this, just to see the dynamics of these atoms or these molecules? Then secondly, is your kind of calculations, is it DFTB? Is it a DFTB calculation you did? So you use material studio, right? Okay, is it DFTB? And if it is DFTB, what particular method, that is the methodology applied for this? And you explained about your absorption, the simulator also that you use. So can you give more light on the actual method you apply?
On your first question, can you do molecular dynamics? It's yes and no. You can actually do molecular dynamics if you're looking for the configurations, which is fine. You can actually still do molecular dynamics to calculate the energies, yes. So because of the level of precision I'm interested in, that's why we didn't do molecular dynamics, but in principle, you can use molecular dynamics as well. It's just that your precision level will not be as precise, and then trying to accurately compare your energy experiment might be a bit. So in essence, if you see some of the energies we got, when we compared with experiments, our energies were very, very close to the experimental value, maybe about 10 kilojoules per mole different. With molecular dynamics, your energies might vary more. Your second question about what I used DFTB. Actually, I didn't use DFTB. What I used was DFT. So there's a difference between DFT, even though DFTB. So the DFTB is sort of a package that implements density functional theory with different approximations. So I used CASTEP and DO depending. So I didn't use DFTB. I hope I've answered your questions.
Someone was first, okay. Can you please come forward so that they can see your camera? Thank you very much. You made a wonderful presentation. Because I want to ask you a lot of hydrogen addition. So I suspect a lot of catalysts, artificial catalysts would have taken place there in removal and the addition. Now, I suspect you would have involved catalysts in both removal and in addition. So I was wondering if you had used organic catalysts like hydrogenasis or dehydrogenasis. Would you have gotten the same result or different results?
So I didn't present on the hydrogenation reaction. The reason why is the current catalyst used for hydrogenation is very cheap. They use, I think, nickel or iron. So those are very cheap catalysts. So we're more interested in trying to dehydrogenation, which is your platinum. So other catalysts is possible, but I wouldn't say for certain. Well, we haven't considered those those catalysts you mentioned, and I don't think they would work. But in principle, you can still do it, but I'm not sure. And the aim of this current study is just to reduce the platinum loading, because platinum is also the state-of-the-art catalyst that's being used. So we just want to reduce the amount of platinum. So every gram of platinum you save is a lot of money. I think platinum goes for about I don't know, about over $2,500 per gram or something. So it's quite expensive. It's more expensive than gold. So every gram you save, it's a lot of savings. So but we didn't consider these other catalysts to mention.
Okay, once again, let's put our hands together for the presenter. So, the question? Oh, please make it brief so that we can go to the next section.
Mine is just is a comment more than a question. I know South Africa has found a niche in the vehicle manufacturing value chain because of platinum.
Yes.
The exhaust system. In the manufacture of analytic converter. Production of hydrogen that has to come from cyclic hexane.
Yes.
I'm now asking because looking at hearing your name, I suspect you are a Nigerian, and I know we have the gas and a lot of petroleum products, which they told us in organic chemistry that it is made of carbon and hydrogen. Is there no way? Because I know the problem here is we have the state-of-the-art equipment to do the research here. Now that you have opportunity of being there, is it not possible that samples can be taken there, research done, and then maybe we become benefactors of the result of such a research on.
Yes.
Okay.
Thank you very much for your comment. South Africa is actually a net importer of petroleum products, and some of the imports come from Nigeria. And this organic molecule I was mentioning, the tricyclohexene and toluene, they are actually petroleum products. But when we say they are clean because we try not to break them up. So, I mean, we're sort of using petroleum products, which is methyl cyclohexane, and we take up hydrogen. So we're generating our hydrogen from water. So we and I don't work there, where we have engineers that make electrolyzers. So we use our electrolyzers to break down this. So yes, we can, a lot of collaboration exists. It can be done like people working together, like in, Professor Pavia and SMA does a lot of collaboration with scientists in South Africa. And I also collaborate with some scientists in Ghana, University of Ghana, and in Algeria. So these are African countries I work with. And I also work with a professor at Nnamdi Azikiwe University. So a lot of times the project is driven by either a governmental need or individual need. So this is just one of the projects I'm working on. We work on projects depending on who is funding us. So I have a project and project partners with people in the European Union, and also this work is sponsored by South African government. So I need that they want us to do. So you have to be very specific, depending on who is paying. Yeah. Thank you.
Thank you, Dr. Obodo. Can we put our hands together for you? Before we listen to the next presenter, let me just do this offline. We are going to listen to Dr. Stella Kamlish, please.
Yes, Prof. Yes. Let me share my screen.
Hello? Dr. Stella?
Yes, Prof. I can hear you.
You are on. You can go ahead and share your screen with us.
Okay. Can you hear me very well?
Yeah, we can hear you clearly. Go ahead. Thank you, Prof.
Thank you very much. Thank you, colleagues. And thank you very much to the organizing committee for giving us this chance to contribute to this 4th African Conference on Applications of Nanotechnology. So my name is Saleh Kamlish. I am a senior researcher at the University of South Africa, and I'm also affiliated with the UNESCO Share Nanoscience Nanotechnology. So the topic of this presentation is laser fabrication of nanofluids with enhanced thermal conductivity. So in this study, we will use molecular dynamic simulations and experimental verifications of the result obtained on this kind of nanofluids. So in general, nanofluids are a type of materials where you add solid nanoparticles inside a base fluid or a heat transfer fluid, which is used regularly in different applications. So by adding nanoparticles as a solid inside the matrix of the fluid, you are able to increase the thermal conductivity. So now you can be able to create a highly performing nanofluid for different heat transfer applications in general. So actually selecting lasers to produce nanomaterials, it's what we call a new way of producing nanomaterials. Let me really take this opportunity to thank Professor Maza, the one who brought this idea to South Africa, and he introduced us to this technology, and we were capable of taking over and trying to do more on this technology of producing nanomaterials by using lasers in general. So what is the motivation? So this is the question. So by using lasers in general to produce, let's say, nanomaterials directly in liquids, so there are some beneficial from that. You can benefit from, let's say, producing nanoparticles in a process which is called a top-down. So you just submit a beam of light or a laser, you have your target inside the liquid, so you can be able to produce nanoparticles. It seems very easy, and it is really easy. So with the same technique, which is laser ablation in liquid, you can do what we call reactive laser ablation in liquids. Of course, you can add some precursors, you can add some molecules. Maybe you would like to do functionalization of the surface of the nanoparticles for some, let's say, nanomedicine or some other applications where you need some molecules to be attached to your nanoparticles. By using this method, of course, you are able to do that. This is what we call solvent precursor target LAL, laser ablation. There is another one where you don't need really a target. You have your precursors, you mix them, and you irradiate with lasers. This is what we call bottom up. You go from the atoms, molecules, and you create nanoparticles through irradiations. So can you see with me that the motivation of using laser ablation in liquid is quite very attractive, because it allows you to do different kind of experiment, which mean this technique is versatile. So that is the first motivation. So the second motivation is, as we know, that materials in general, solids, they have higher thermal conductivity than liquids. So from what we have observed in the literature, we found that there are quite a number of metals and metal oxides which they can be used due to their high thermal conductivity to be ablated to get these nanoparticles inside some base fluids, as you can see from here, like water, ethylene glycol, mineral oils. As you can see from this, that these, let's say, conventional heat transfer fluid, they have lower thermal conductivity. And unfortunately, this is what is used in industry now. I remember some other presentations, particularly the presentations of Prof. Maza. He mentioned about the use of ethylene glycol in cars in general as a heat transfer fluid to cool down the engine. So we can be able even to add nanoparticles of these metals, and this is ethylene glycol, and we will really enhance the thermal conductivity of this material which is used in industry. I will discuss with you more about this during this presentation. So that is the second motivation. Now, the third motivation, why we need to use lasers to produce nanomaterials in general or nanofluids as advanced heat transfer. As you can see from these figures here. So let's now think about this, say, from the business perspective. So now there are some scientists, they will state that, okay, lasers are very expensive. I agree with you. The lasers are very expensive, particularly if you are targeting what we call pulsed laser ablation. So you need high power lasers. Of course, in Africa, it's difficult to raise the necessary fund to get these lasers. But at the fundamental level, of course, it can be expensive. From this figure here, it shows you clearly that the laser ablation in liquid compared to chemical reduction or chemical methods. So as you can see, the chemical methods, they appear here, the production of nanoparticles by chemical, it appears cheaper from this yellow line, sorry. But now you can see that the laser ablation in liquids, the green line, it seems like expensive. But now, if you are targeting to produce like some milligram nanoparticles for industrial applications, there is a threshold where the mass, when it is getting higher, the cost of the LAL is become lower than chemical reductions. You will ask me why. Chemical reductions, of course, when you produce your nanomaterials, you have contamination, you have salts, you have different things. So now you have to go through purification process. With laser ablation in liquids, you don't need really to do what we call purification process, because you are producing highly pure nanoparticles in your material. And you have the choice to add, as I mentioned in the previous slide, to add molecules to the functional laser, functionalize the surface of the nanoparticle, which mean here, we can use lasers to study at the fundamental level, but for us to go for industrial level, it's really interesting to look at laser ablation in liquids. And this research, it was done by a group, which the paper it is stated there. So now there is another one here. Recently, lasers in general, or ultra-fast pulsed lasers, this shows that the technology is getting much cheaper now. As you can see from this figure, the power, this is the power and watt of the existing lasers. So now higher powder, so the relative price is going down. So now in the, I am very optimistic that lasers, they will get much cheaper. So for us as African, I think it will be very beautiful to embark in this kind of research, because it will allow us to go further, to produce materials to be applicable for us here in Africa in general. So what we are doing here exactly, it's very simple. You need a source of laser. In our case, we use what we call in-diag lasers, which they work at a wavelength of 1064 nanometer, which means at the IR or at the near IR. So you have a beam of laser, you reflect it with a mirror, you have a lens, you have a target, you have your liquid, and you do your experiments, you control rotation, because you cannot do ablation on one spot, otherwise you will dig deep and you will not produce nice nanoparticles. Of course, you control the rotation, you control everything. And this is just a demonstration here of which will work. I'm not sure it's not working, maybe of the internet. But anyway, that's fine. So this video here, what it shows you, the process, what we are doing. Unfortunately, it's not playing here, maybe due to the internet. Our internet is quite low, but in general. So in this method, which is laser ablation in liquid, you can select different kind of targets. In our case, we use it silver, we use it gold, we use it aluminum, we use it copper, molybdenum, graphite. We manage to produce different kind of nanoparticles in ethylene glycol and water and synthetic oils. So the laser parameters are stated there. In the laser, of course, 1064, the laser energy we use it, so all the parameters are there, and we manage to produce high quality nanofluids, as you can see from this figure there. So these are some results, high resolution transmission. As you can see with me here, it's clearly showing that for the copper nanoparticles are, as you can see, are very narrow there. And if you look at the particle size distribution, so the average size is around 7 nanometer for copper nanoparticles, using the same parameters that I showed you. For the silver nanoparticles, actually they show an average size of around 12 nanometer, which are a little bit bigger than the other ones. And you can see the rings from the selected area electron diffractions that the nanoparticles are crystalline. Of course, these results are coming from studies of our PhD students and the UNESCO research share, Mr. Mpampo and Ms. Toreya Khamlishi. They produced very nice results, of course. And they published this work already in scientific reports and some highly cited journals. So let's now look at what is happening during the ablation. You put your target, as I mentioned, you put your liquid, it's very simple. You have a beaker here, or you can design a very sophisticated system to avoid splashes and stuff. So the laser is coming to the target. Very fast, at really, let's say, at the picosecond regime, the laser will touch there and the plasma is created at that regime. So a bloom of the target, it shows there. It shows that there is an ablation of the target inside the liquid. So when the time is moving up, of course, the bloom, it's caused due to the evaporation of the metallic targets, atoms, ionized atoms there, which means this bloom, of course, it has very high temperature. Imagine with me, it can be to thousands of degrees. So that temperature will cause the layer of the liquid at the surface of the bloom to create what we call a vapor layer, a vapor of this liquid surrounding this bloom. And the bloom, of course, is expanding. And during this process, I put this figure down here because I didn't mention here what we call shock waves. Shock waves, of course, they happen there while the plasma, it is going up. And of course, we have down here the melted material. So the melted material, because you have pulsed laser, a pulse and another pulse is coming, another pulse is coming in a faster way. So you have a melted material, another pulse will cause this material to evaporate, another pulse will come. So it's a local heating and evaporation, what we call it. So of course, at this stage, this plasma, it will start to shrink and the cavitation bubble, it start to go up, and some materials, or nanoparticles, they start to be created. So once this plasma, it will go down and shrinks totally around the microsecond regime, at this regime, so you will have nanoparticles there inside the bubble. And once the bubble collapses, you will have nanoparticles inside the liquid. And you are more than welcome to go through this paper to read more about the mechanisms that we explained more about the phenomenon happening. So the mechanism, this will repeat during the time when you are doing your pulsed laser. Of course, making your material now, we need to understand, because our target is to produce nanofluids or advanced heat transfer fluids for applications as coolant or as heat transfer fluid for solar energy applications, let's say. So now for us to be able to judge our material, we started doing some computational modeling to look to the contribution of the metallic nanoparticles to the enhancement and thermal conductivity of the liquids. So what is the process? We're trying to understand through computational modeling or molecular dynamic simulations. And we have done that, we obtained nice results, and we have done experiment to prove that the molecular dynamic simulations, it's really a good method which can allow you to study what we call thermophysical properties of nanofluids or nanomaterials in general. So what we have done, of course, we have two systems that I was speaking about, which is copper and silver. So at the beginning of the molecular dynamic simulations, of course, you have to create what we call a box which contain the materials that you are interested by. By the way, thanks to Prof. Rao, who shared with us his knowledge and the theory behind the molecular dynamic simulations. Of course, I'm not going to go deep in the theory here, but I'm going to share with you an overview so we can be able to use this technique to study thermophysical properties of your material. So for the copper nanoparticles in glycol, we created this box here, which have, let's say, because we're trying to study the impact of these nanoparticles on the heat transfer of ethylene glycol. Of course, we added molecules of ethylene glycol and a particle of copper there. And this particle, it has 7 nanometer in size. And of course, the box, the size of box is 100. It's a smaller box. For the silver, we use the bigger box because during our calculations for this system, a smaller box doesn't give us really good stuff. So so that's why we're pushing to create a bigger box with 500 Armstrong, so in order for us to get more reliable data. So for you to be able to create these molecular dynamic models to study your materials, we use what we call atom scale. It was created by a French institution. I apologize, I forgot the name of the institution, but it was created by a French institution. It allows you to create solid materials like these nanoparticles there. The PACMOL, it's a package also. It relies on coding and stuff. It allows you to create liquids like this. Because at the beginning you create a molecule, but for you to create a liquid from a molecule, you have to use what we call PACMOL. So to create a solid and a liquid, so you combine between these two packages. So again, the video is not playing here. I want to show you what is happening to the system, because remember with me, heat and material science is vibration. Heat is vibration. So by using molecular dynamic simulations, we apply some energies. So this molecule vibrates, you apply more energies and you look at the behavior. And from there you can extract this term of physical properties. But atomic interactions, of course, at the liquid matrix or for the ethylene glycol or the potentials used for the solid materials are stated here. So for us to be able to simulate this system, of course, we have to take into account the potentials. It's very important because without using the right potentials, interactions between these atoms, it's not going to be right. So which means you will not be able to get reliable data at the end of the day. So for the ethylene glycol, we use it, what we call Leonard-Jones potential, which is very well known, which is this one. It shows you clearly the interaction between atoms within that system or the ethylene glycol system for carbon, hydrogen, and oxygen. So for the copper nanoparticle, of course, I'm giving one example here. I didn't show the silver one, but for the copper, we use it what we call embedded atom model, the EM potential. I'm sure our colleagues who are dealing with molecular dynamic simulations, they will understand very well the reason of using the Leonard-Jones for molecules at the liquid stage and for the embedded atom model. Of course, interactions for metals is different from liquids in this case. That's why we combine and we use different, what we call potentials. So before, of course, you have to show the potentials used during the calculations. And as I put here, we use it what we call, for the calculations, we use it algorithms, which can be used for the large-scale atomic molecular massively parallel simulation, LAMPS. It's very well-known package also. So this package, it has algorithms based on Newton's equations of motion, of course, and Verlet algorithm, as Prof. Rao showed you before. So that is classical physics, by the way. Prof. Rao, it shows you a combination between both classical and quantum. So in this case, we use it mainly classical physics, only Newton equations of motions, Verlet algorithm, which can allow you to follow the movement and the steps of these molecules moving around. As I stated previously, heat is vibration. So that algorithm, it allows you to follow the trajectories of these molecules, so you can be able to extract what we call heat transfer, and you can extract the thermal conduction of the day. So, but before showing you that, I want to show you something very important. So before carrying the calculations of the system, we have done what we call radial distribution function, just to show to the scientist that our particles which was used, it's really a solid. So for a solid particle, if I look for the radial distribution function, of course, this is a model. So the structure, as you can see here, of this solid copper has regular periodic structure. This is what it shows here, which is a crystalline nanoparticle, even if it's a model, because as the beauty of these techniques, you can simulate a real, let's say you create a laboratory in your computer. This is what you do. You are creating a laboratory in your computer. So the molecular dynamic is like you are doing an experiment, but a virtual experiment. This is what we mean by that. So for me, I have to confirm that this particle is a crystalline and it is a solid. So if I have this periodic structure which shows here, it means that is a solid. But now for the liquid ethylene glycol, the behavior is different. So the molecules become independent of each other in this system because they are not really connected, the molecules in the liquid. So, and the distribution of each atom within this molecule of ethylene glycol return to the bulk density of 1, which confirm the liquid nature of the model used in our calculations, which means now we are confirming that our nanofluid, it contains a solid nanoparticles and a liquid, of course. So what we have done to extract the thermal conductivity from this beautiful model? We use it what we call equilibrium molecular dynamic simulation integrated with green Kibo method. The equilibrium molecular dynamic, what we do, we equilibrate the number of atoms, we equilibrate the temperature and the pressure within the system. So, and of course, the green Kibo method, it's very well known, it's used, which is integrated with this equilibrium molecular dynamic. It allows you to study thermal conductivity, as you can see here, and also viscosity of the system. But now we use this method to study only thermal conductivity. So the thermal conductivity equals the volume of the box I showed you, is this one, divided by the Boltzmann constants and the temperature of the system, times the integral of the heat transfer within this system. As I mentioned to you, heat is vibrations. So for me to be able to extract the thermal conductivity, I have to plot what we call the heat transfer function, which is this one down there. So the heat transfer function, it has the kinetic energy, the potential energy, the enthalpy. It has, of course, the force applied on the system because you have to apply a force to create vibrations. And this is a model, computational model. It's not in real life. In the real experiments in the laboratory, your system has vibrations because even at room temperature, it has vibrations. In a computational modeling, you have to apply a force in order to have this kind of vibrations. So that's why you can see there the heat flux autocorrelation function. It shows you these oscillations. We apply the force, the oscillations are high, and the system is going to equilibrium. So once we get the heat flux autocorrelation function, you do integration at this area, you extract your thermal conductivity. But for you to get a symmetric heat flux autocorrelation function, you have really to make sure that all your parameters during the calculations are right. So you can be able to extract this heat flux autocorrelation function and you can use it to calculate the thermal. So this is what we have done in molecular dynamic simulations. Of course, I'm not going to show you now the results. I will show you the results later. Now I will show you what we have done to confirm the results of this molecular dynamic stuff. We use this technique. We built this apparatus at Tempa Labs in Cape Town with the help of course, eminent scientists at the Material Research Department in Tempa Labs, National Research Foundation, Professor Doyle and other professors, they were working with us. We managed to create this cylindrical system. They call it hot plate system, or a steady state method, they call it. So of course, doing modeling, it's fine and nice and beautiful. But now the scientific community, they will ask you one question. Did you prove that? So yes, we are proving that. We build systems to prove that. So by using the one-dimensional heat conduction equation, This equation I see here, this equation, it helped us to build this system. So here can you see the heat flux equal the thermal conductivity times the area of the plate divided by the distance between the plates. This is the first plate, this is the second plate, or this is the hot plate and this is the plate. This is the hot plate, this is the hot plate. So the D is the distance between these cylinders here. So if you have all of these, you apply the power, you heat your cylinder, so that heat which is generated here is the heat flux. And we know the power here in our case, because we are applying the power. So the ambient temperature, because if you are going to use your nanofluid, let's say for concentrated solar power. So now the ambient temperature is very important because it impacts the thermophysical properties of heat transfer fluids or nanofluids. So we vary the ambient temperature by this system here. We push here water at different temperatures so we can be able to do this thermal conductivity analysis at different temperatures in general. And we have all the parameters. So now what we need just to extract what we call the thermal conductivity and compare it with the molecular dynamic that we got. So these are the results that we got. So I'm showing you here just the efficiency, the efficiency, the heat the enhancement efficiency in thermal conductivity. You can see from this figure here the copper nanoparticles in ethylene glycol, which was ablated for 5 minutes with lasers. So the experimental is the blue line. That is, sorry, that is the efficiency. At different temperatures. But now the molecular dynamic analysis, it shows you that it is really, it's almost close to this, to the experimental one we have done with the hot plate system. Molecular dynamic, it gives us also very nice stuff. If we take the case of the silver, it shows you the experimental, and it shows you the molecular dynamic. So some of the scientists will ask a question. So why we need to use this molecular dynamic if we can extract the data experimentally? So now imagine with me, you would like to study this kind of fluids, let's say 1,000 degrees. So you cannot do it at the lab. It's difficult to build a system to do that. So if we confirm it that the molecular dynamic, it allows you to study thermophysical, which means we can study highly advanced systems at harsh conditions, and we can extract reliable data, as you can see from here, which means we can do studies on different systems, particularly with this COVID, and most of the students are working from home, and researchers, it is fantastic to create a nano laboratory in your computer and try to study different materials. So once this COVID is out, so we can go and do experiments and prove that we are capable of studying different functional materials or nanomaterials. For the copper, it shows 24.16% in enhancement. For the silver, it shows 30.16 in enhancement. Which is beautiful. I'm showing you here at different laser ablation times. So more you do ablation, more time, which means you increase the concentration of the nanoparticles. That's why you have more enhancement, because for the simple reason, you are increasing the concentration while you are increasing the time of the ablation. Can you see that this laser ablation technique, it's really fantastic. It produces high quality nanofluids for applications as heat transfer fluids. So, of course, the ongoing research, we are not going to stop at the fundamental level. We have really to study this nanofluid for industrial level, for development in general. So we created this system at the Tempa Labs again with students there and engineers at the Tempa Labs. So what we want to try to do is to study these nanofluids for real life applications. This is what we call a small scale concentrated solar power system. So what you do, you harness the sunlight, which is coming, you reflect it on a tube. This tube, it has a selective solar absorber coated on the surface. You pass your nanofluid and you study heat transfer, because you have probes here that they can allow you to sense the temperature. If you know the temperature of the inlet and the outlet, you can judge the efficiency of your nanofluid. So this work is still going on, and due to the COVID, so we are still trying to find the time to continue. Of course, this nanofluid, you can use them. We didn't start on this, of course, but from this paper, we found that nanofluids are used also for solar photovoltaic systems, panels. You can cool them down with these nanofluids very simply. I think these are Mexican who have done this system. So, and can you see with me, these people, they use silver nanoparticles, and you know silver nanoparticles are good in thermal conductivity. So they produce their materials with a chemical method, of course, they didn't use lasers. Look with me here, this picture, what they found with the nanofluid. So the panel, the solar panel, this is the time during the day. So when the sun is high, so the panel without cooling, it has a power of less than 45, I think. But now with the cooling, can you see with me, the power is just high. And so now you will ask a question, why we are not using this technology to harness more energy from the sunlight? So it shows clearly that these nanofluids, they have a huge benefit when it comes to enhancing the performance of either concentrated solar power systems or solar PV in general, as I showed you here. And now for those who are interested by batteries and energy storage. So there is another study, it shows clearly that for batteries, of course, we know all of us, when they got hot, so the performance is not good. So now we need to make sure that they are working at a lower temperature, so we can have a highly efficient battery in general. So by designing a battery and putting some micro channels where you can maybe inject your nanocoolant or nanofluids from these simulations here, as you can see at the top here, it is water ethylene glycol, and this is water ethylene glycol without nanoparticle, which means it's not a nanofluid, just a heat transfer fluid. But now when you go down there, you can see that the cooling, when you add the aluminum oxide, the cooling is just beautiful for the battery. And this study shows that the battery was working in a high efficient way when you introduce micro channels to cool it down. This is simulation. So we are looking also in the future to see how we can implement this for energy storage, of course. And cars or nanofluids for electromobility, of course, there are different parts in your car that you can use nanofluids, of course. Currently, we are going to the electromobility. We use electrical cars. So now the heat for the batteries is going to be huge. So nanofluids market is going to be also huge. So we can really produce nanofluids in a high efficient way if we can use lasers. As I showed you at the third slide, that the cost of using laser ablation, it's lower when you are targeting industry, not fundamental research. For industry, it is wise to go for this technology of nanofluids, so we can create a market in Africa to produce nanofluids. Particularly the European now, they came and they invest a lot in Africa in producing cars. So we can think about that also in the future. So as a summary of this talk, what we do molecular dynamic or computational approach to study our nanofluids, of course. We do experimental, of course. Lasers are difficult to get in Africa, in South Africa. Of course, they have CSIR, they have UKZN, they have lasers. At the Tempa Labs, the Material Research Department, thanks to Professor Maza, who bought some lasers there. So now they will allow us to do more research on that. So we do both. So we can create highly efficient nanofluid for academic research and also for industrial applications, as we mentioned. So acknowledgements, thank you very much. Thanks very much to the National Research Foundation for funding this research. Thanks very much to the UNESCO UNISA Africa Share Nanoscience Nanotechnology for also contributing financially and technologically to this project. So the part of the work was also supported by the Nanoscience African Network, Nano AFNet, The Tempa Labs, of course, are very grateful that they are allowing us to do different kind of research there. So, so this is fantastic. And thank you very much to Mr. Mpampo and Ms. Choreya, PhD students who have been doing fantastic work on this laser ablation and liquids to produce highly efficient nanofluids. And thank you very much. Hello, any questions? Any questions, colleagues? I got some questions here, but I'm not sure if the share will conduct. So the chair is he around? The chair? Who is the chair of this session? Hello, any question? So I saw a question here from Phoenix. He is asking, please could you explain the concept of efficiency? So may I answer that question? When I say efficiency, let me give you an example. So now you let's say you want maybe to create a system to harness the sun energy and to convert the sun energy to heat. So that heat that you are generating, it has to be transferred efficiently. So if you use conventional heat transfer fluids, like let's say water or ethylene glycol, of course, liquids, they don't have high thermal conductivity. By introducing nanoparticles, you increase the efficiency of that conventional heat transfer fluid, that water or ethylene glycol. So you increase the efficiency of that heat transfer fluid itself by introducing nanoparticles. This is what we mean, because solid nanoparticles, they have high thermal conductivity, the liquids in general. And if you can use nanofluids, which means the heat which is generated, it can be removed efficiently. It can be used for your application that you are interested by. So hopefully I answered your question in Phoenix, yeah, hopefully. Any other question, colleagues? So if there are no other questions, thank you very much to the organizing committee. Thank you very much to all the researchers involved in this project of the nanofluids here in South Africa. Thank you very much to Prof. Izima, Prof. Kinit, also Professor Maza, our role models here in Africa. As emerging scientists, we have to follow the steps of these giants. Thank you very much, and hopefully we'll contribute to this beautiful event in the future. Thank you to everyone. Thanks. Have a good day.
Hello, is it time for my presentation?
Army Research Office, and a military scientist and engineer from Fraud CCD with a mission to identify, advance, and transition fundamental science and technologies that contribute to Army modernization and prepare the US DoD for the battlefield of the future. Previously, Dr. Bray spent 2 years as the Assistant Secretary of the Army for Precision, Logistics, and Technology. Working in research and technology, Dr. Bray worked across the entire Army S&T portfolio, including serving as the Deputy Portfolio Director for Network and Environment and Terrain. He also served as the Army representative to the DoD High Performance Computing Modernization Program Advisory Panel, providing direction from the executive steering group to the program. Dr. Bray was the liaison to AXAAL team from the U.S. Army Engineer Research and Development Center, ERDC, guiding the ERDC through the implementation of the Army modernization priorities, cross-functional teams, 9 corps, and stand-up of the Army Future Command. During his time at ERDC, Dr. Brame was the team leader for the material science team in the chemistry branch of ERDC's environmental lab. Dr. Brame led an interdisciplinary team studying application and environmental health and safety implication of advanced materials and nanomaterial for the Army. He formed and served on the board of the Intelligence Water Treatment Working Group with scientists from 10+ federal agencies and departments. Dr. Brame's degree are in physics, BSc from the Brigham Young University, and civil and environmental engineering, PhD from Rice University, and he has more than 20 peer-reviewed publications, and he has presented at dozens of research conferences and scientific meetings. I welcome Dr. Brame for his presentation. Dr. Brame, over to you.
Well, thank you very much for that kind introduction. There was a lot in there that may not be relevant, but I will maybe highlight two things. One is that I have spent almost 2 decades now studying nanotechnology, and I'm very excited and honored to be able to share some of that with this conference today. So a big thank you to the conference organizers and to everyone attending. Number two is for those who were able to attend the Monday session, I shared a little bit of information about the ways in which the US Army and Department of Defense is interested in funding researchers in the field of nanotechnology and in many other fields. Usually we do academic visits, and with all of the virtual technology now available since the pandemic, we're able to virtually visit with people. And so if you are interested in learning more about those opportunities, I would invite you to please send me an email. Here's my email address. Note the ON at the end of Jonathan, a slight unusual spelling. And we can set up a virtual meeting with you, with your university, to talk about some of those funding opportunities. But the focus of today's talk is on the technical work that I did prior to starting as a program manager with the US Army. Specifically today, I want to focus on this publication from Environmental Science and Technology, looking at photocatalytic water treatment. It was a joint publication with many other co-authors. If you are familiar with this field, you'll recognize many of the names here on the list of co-authors. And the concept for the publication relates to this picture here on the screen. If you see a static picture of the sun near the horizon without any indication of time, it's impossible to know whether that sun is rising or setting. And so in 2018, this group of esteemed researchers gathered at the ACS conference in New Orleans in the United States and tried to look at the technology of photocatalytic water treatment and assess, is that a technology that is rising and has a great career and future in front of it? Or is that a technology that is setting, in that most of the science has been done and the technology is unable to break into the real world? There have been certainly a lot of publications, but not a whole lot of implementations of this photocatalytic water treatment in real world settings. And so we had 2 days of fabulous conversation. Some of these researchers have been studying this field almost as long as it has been a field. A lot of experience. We were able to talk a lot about the work that we all have done, but also set aside our individual research projects and take a look at a field as a whole to try to understand where it is and where it is going. Again, is it rising or is it setting? So I'll start with just a little bit of introduction. If you have been attending the meeting today, you've seen some of the background material, so I'll go a little bit quickly. What is photocatalysis? Basically, it is a catalyst, a material that can convert light energy, photons, into chemical energy, reactive oxygen species and redox reactions that can be used to remove harmful chemicals, bacteria, etc., from water. The typical version of that is a semiconductor photocatalyst. And so if you have photons of significant energy to match the band gap of the semiconductor. You excite an electron from the valence band into the conduction band, create an electron hole pair. And if that exciton doesn't recombine back and release the heat as energy, the electron in the hole can participate in redox reactions. And so that's basically the technology that has been studied. There are a lot of potential benefits of this technology. One being lower material cost. A catalyst can be put into a system and maintained there for a very long period of time. And so you don't have to add additional materials. That decreases the logistical burden. You also can use sunlight as your energy source. So that can be free and abundantly available. Additionally, there's a very strong redox reaction here, particularly when using UV light as the excitation, creating hydroxyl radicals. You get a lot of power in those redox reactions. So you can degrade recalcitrant pollutants, some of which are very difficult to remove in any other way. So this technology has been studied for quite a while, 35 years or more going back to the mid 1980s. And there have been many, many studies and many publications. In our publication, we tracked the last 20 years worth of publications in the field, looking specifically at photocatalysis and water treatment. And we found an exponential increase in those publications. Lots and lots of interesting work, interesting science. Looking at the last year we had data available, which was 2017, there were about 1,400 publications in the field. But when you break down what exactly those publications are looking at, when we add keywords to our search, we add titanium dioxide, for example, as one of the primary photocatalyst materials. That's about half of the literature. When we look at visible light, and we'll talk a little bit about why visible light is important, again, about half. But when you start to look more closely into applications, things like reactors or pilot systems, the number of publications drops off precipitously. There's a lot of work being done in the science and not a lot of work being done in the application of photocatalysis for water treatment. And so that was one of the things that we looked at is why is there a disconnect there? Is it because this is not a field where applications can be readily adopted? Is this because this technology is not well suited? Or are there other reasons? So we started by looking at some of the challenges. If you look at the process, in general, you have to take light. So again, you could use sunlight. You can also convert electricity into man-made light using either UV lamps or LEDs. That light then gets into the system and you lose some of the light either through scattering or because only a small fraction of, for example, the solar spectrum is usually utilized in photocatalysis. Then the photocatalyst itself can only absorb a certain amount of light. Some of the light is reflected or lost in other ways. You do create some of these electron hole pairs, these excitons that can sometimes recombine, and you lose the energy as heat. Even once you make reactive oxygen species, some of those reactive oxygens can be scavenged by other materials in the water. And so at each step from the photon all the way through the contaminant degradation, you're losing efficiency all throughout. And so when we did some calculations to determine how much of that energy efficiency are you losing, and you're losing anywhere from, in the best case scenario, losing 95% to, in more realistic scenarios, you're losing 99+% of the available energy. And that can be problematic. That can make it hard to run an efficient system. That can make it cost prohibitive. Even if you're looking at a situation where you have plentifully available sunlight as your power source, your source of photons, there still is a lot of loss in those systems. And that can cause problems for creating a real world system when you're not just testing small quantities in the lab. I will note, as this conference is focusing on nanotechnologies, there are many, many opportunities throughout this process to improve the efficiencies by using nanotechnology. And we've heard about some of those from the speakers this week, everything from harnessing solar energy to improving LEDs, et cetera. So a great opportunity for additional research here. Some of the efforts over the years to advance photocatalytic materials, focus specifically on the materials. there's been a lot of effort to modify and improve titanium dioxide. Titanium dioxide is far and away the most common photocatalytic material. It is inexpensive, it's plentifully available, it's a very robust material, it's easy to make and manufacture, it's relatively inert to humans. We even add it to our food products and makeup and other things. So it's kind of the elephant in the room, but it does have some limitations. For example, the band gap of titanium dioxide is rather large, meaning that only UV light can excite titanium dioxide. And UV light is a very small portion of the solar spectrum. And so if we want to really access the efficiency of the energy provided by the sun, we need to find ways to use longer wavelengths and therefore shrink this band gap. So a lot of work has been done in finding ways to decrease the band gap for excitation. Usually that's done in ways such as doping. You can add transition metals or non-metal dopants, N-type and P-type in the semiconductors to shrink that gap. We also have done a lot of work as a community in heterojunctions and sensitization, also trying to enhance the wavelength of utilization of light. There's also been a lot of work in trying to reduce the recombination. As I mentioned before, many of the electrons that are excited then just recombine back with the holes, releasing that energy as heat and not doing any work in reducing the contaminants in the water. So we've looked at many things, including adding metal junctions to withdraw electrons, Schottky barriers, and also things such as very fine control of the structure of the material to try and enhance electron transport within the materials and allow the redox reactions to happen more quickly to avoid recombination. So lots of work there. There's also been a lot of work done in non-titanium dioxide materials trying to expand beyond TiO2. We saw some of that earlier in the meeting this morning. A lot of different options. I've listed just a few of them here. Some of them have great advantages. Some of them are naturally able to harness more wavelengths than just UV. But there are also drawbacks to many of these materials, things like toxicity, chemical or physical stability. Sometimes they're very high cost, which if you're looking at a true catalyst could be overcome by many, many reuses, but they can be quite expensive. And so it seems like every material has its pros and also has its minuses. And so as we kind of move beyond the titanium dioxide and trying to understand what are the next steps to take this from the lab out into the real world, a few things we need to look at. One is whenever we as scientists do studies on these materials, we need to better assess some of these characteristics, things like cost, stability, robustness, ease of separation, to better understand not just how does this material work in the lab, but how might it work in the real world. We also need a standard assessment measure. Most of the time, the assessment that is provided for a photocatalyst in water treatment will provide things like the percent removal, which is important. We want to show a large amount of removal of contaminants. But if you don't know whether that removal happened over the course of 5 minutes or 10 hours, it may not do a lot of good. If you don't understand the mechanism, it may not do good. Sometimes we can create byproducts as we partially degrade a contaminant in which the byproducts are more harmful than the original contaminant. So we need standard assessment measures that will allow us to compare materials against each other and also allow us to implement those into real systems. So taking the next step towards real systems, talking a little bit about reactor design. Far and away, the vast majority of photocatalytic testing happens in batch reactors, small scale, bench scale batch reactors. That's where I did most of my studies as well. They have a lot of really important advantages, particularly when you're looking at science. They're very simplistic, very well mixed. You have good mass transfer, you have good photon absorption. It's easy to test your materials. However, as we start to move towards application, there's a lot of non-realism about that. We can't treat water in 100 milliliter batches in any real world application. And we also have to be able to remove the photocatalyst. And if we're mixing particularly nano-sized photocatalysts directly into the water, that can be very challenging to remove. So there are some issues there. The next kind of the next step then beyond that to try and move into more real world scenarios is to immobilize the photocatalyst. And that can be done in a number of ways. You can immobilize catalysts onto a larger carrier that can then be mixed, such as in a fluidized bed. And then these larger carriers can be more easily separated out from the treated water. You can attach the photocatalyst to a membrane or to the reactor walls. Therefore, the photocatalyst stays put as the water moves past it. You can even attach it to fibers, fiber optics, or electrospun fibers. A lot of different options there. Of course, that helps with removal efficiency and gives you more options for the design of reactors. But there are some disadvantages as well, particularly if you're looking at nanomaterials. They have a very large surface area, and when you attach them to something, you lose a major amount of the surface area already. That can decrease the illumination and also the area available for reactions at the surface. It also can increase scattering, increase fouling, and there are a lot of other obstacles to be overcome, but certainly moving in the right direction. Some other areas in which both now and in the future people continue to move is to increase use of LEDs. Again, we've talked a little bit about that in this conference. LEDs have a lot of advantages. They require very little power. Also, by using photovoltaics and other technologies that already access a little bit broader of the solar spectrum, you can harness energy from the entirety of the solar spectrum and then use that energy to power LEDs at a single wavelength that may be most advantageous for your reactor system. And in that way, you can get an increased efficiency without necessarily needing or having a broader spectrum that your catalyst is using. And then improved means of comparison. I talked about this already. One of the things that's really salient for publications is understanding the reactors. And so, for example, understanding the photon absorption normalized to volume. So how many photons are creating the impact that you're citing in your paper. And also understanding this concept of electrical energy per order is the idea of how much energy does it take to remove 90% of a contaminant. And that can give you a good idea of, first of all, is it scalable, right? If we need to remove contaminant, how much energy is going to be taken? But also it allows a better comparison of, if I removed 90% of this contaminant in 10 minutes versus in 10 hours, how much energy was required to do that? That may be a different story if you have a stronger bulb, more light fluence, et cetera. So better means of comparison. This kind of brings me to the conclusions of the paper, the recommendations of the authors as we created this, this review. A number of those recommendations. So one is to expand the criteria for assessing the performance of treatment systems. We mentioned already how important it is to include information about cost, availability, and feasibility, even when you're doing a basic science study. When generating a brand new material, if you don't address those things, then really you're leaving out the potential for application down the line. Second is to evaluate the performance of the photocatalysts under well-defined conditions. It's amazing how many publications are published in the literature that don't specify very important components of the system that are required to really analyze how well the system is working, particularly when it comes to illumination. A lot of times people will provide maybe the power of their light source and that's it. And we don't understand the photon flux. We don't understand the spectral variance within the lamp. There's a lot of information required in order to compare. Similarly, using relevant probe compounds. Dyes, for example, are a very good target because it's an industrial problem. It's a very real world application, but dyes also interact strongly with light. And therefore, if we're trying to understand the photocatalyst system, if you're looking at a photocatalyst, maybe use a probe compound that it does not interact with light so you can better understand it. And then things like normal solution conditions, pH, ions, scavengers. Scavengers is a really important thing as well. I think a lot of the time when we analyze water treatment, we look at a single probe compound, maybe 2 or 3, and we do it in clean water. But what happens if you add just even a little bit of natural organic material? Sometimes you can remove most, if not all, of the impact because that organic material will soak up all of the reactive oxygen. And you won't be able to degrade nearly as much of your contaminant. The next chat. The next recommendation, to consider creative approaches to new materials, but don't neglect the specific challenges in the field. I think it's easy sometimes to look at a new material that's being used for photovoltaics and say, well, if it's photoreactive, why don't we use it as a photocatalyst? But that may ignore challenges such as, for example, if it's soluble in water, it won't work as a photocatalyst, even if it's great at creating photocurrents in air. And then last is to design and test materials for specific applications. I think sometimes it's easy to paint with a broad brush and say, well, this could be used for water treatment and everyone needs water treatment. But we've already talked quite a bit about the fact that there are not a lot of real world applications and hardly any large scale real world applications of nanotechnology that are currently in use. And so it's okay. And I think sometimes it's preferable to say, what are the specifics about this process that could be used in a niche application as opposed to a broad application, because that may be a more likely landing place for the technology. That is, in fact, one of the primary recommendations from the whole of the paper from all of these experts, is that large-scale implementation seems to still be a ways away, and we're not pushing on it right now. But niche application may be where this actually has an opportunity to gain a real foothold, particularly when utilizing the unique benefits photocatalysis has to offer. For example, solar applications. If you're looking at water treatment in a dense urban environment, it's unlikely that you can use the solar benefit of free power for your system. However, if you're looking at point water treatment in rural communities, that may be a great option because you have plenty of space to harness the solar energy. Similarly, reduction, both reduction and oxidation happens. Most of the degradation happens through oxidative pathways. But given that there's strong reduction potential, we can also utilize that for niche applications. There was a great example this morning of hydrogen evolution as a byproduct of contaminant degradation. So that may be another option for application. And then pre-treatment, there may be some industrial processes where you have a really strong effluent that needs to be treated and knocked down so that it can be treated using traditional water treatment processes. So coming back to the question of sunrise or sunset, I think that we concluded that it would be unfair to characterize this technology as a sunrise. It's been studied for a long time, and they're just not the real world applications that are happening with any large amount. But we also don't necessarily think that it's a fair characterization to call it a sunset. Looking at our graduate student, who was the primary author of the paper, standing on the beach and looking at the sun, we decided to look at technology through this lens that's often used to look at many technologies, not just water treatment. But if you look at a time along the x-axis, and the y-axis is expectations for the technology. And again, this could apply to any technology. It seems that usually there's a period of positive hype. This is the time when the technology can do no wrong. It's going to solve all of the world's problems. If you put that technology in your proposal for funding, it's most likely to be funded. And that can create a peak of inflated expectations where we thought it was going to solve all of the world's problems. And then when it doesn't, there becomes this negative hype where people then start saying that, well, it doesn't pan out. It's not worth pursuing. There's problems. There's no real world applications, for example. And that can lead to a trough of disillusionment where it could be a full sunset and the sun disappears, the technology goes away, and we move to study other things. Or maybe from this more realistic point of view, we can then move forward towards, again, niche applications and practical expectations where we find the things that this technology is most suited for, and we have targeted application there. And we don't try to solve all problems for all people, but we solve the problems that this technology is uniquely suited to solving. So that's a very useful paradigm to study any technology. And as I look at my career in water treatment research, I took a number of my publications and I tried to plot where they might fit on this graph. So forgive me, there's rather a lot on this chart. So each of the little boxes is one of my publications in the field. Along the kind of the general x-axis of the whole chart, it goes from basic research on through to full-scale implementation, which I've not studied at all. And then for a few of these publications, I also tried to say where on this graph of hype, inflated expectations, negative, trough of disillusionment, and progress, where on this graph do my publications sit? And I found some of them certainly contributing to the positive hype, thinking that this is going to solve all the world's problems. Some of them also contributing to negative hype, pointing out the difficulties and the challenges and why this may have some problems being applied. Some of the more interesting publications, though, came as I looked at some of the actual and potential real-world niche, maybe very small, but real-world applications of the technology. And I think these are the ones that are more likely to have impact in the future. And so, as I wrap up the technical talk, I would leave this as a call to action. Whether you are an esteemed professor with hundreds of publications that you could chart, or whether you are a graduate student working on your first publication, I want you to think, where are you working on this chart? Are you working in the positive hype? Are you building it up? Are you working in a realm of inflated expectations? Are you working in a field that's rapidly in the decline and maybe in the trough of disillusionment? Or are you working in an area where there are real world applications? I think there's value in each of those arenas, right? There's great value in doing science for the sake of science. There's great value in the things that we learn, even if the application takes a long time or in some cases never comes. But if you are not at least eyeing that future and at least thinking, how will this actually be used, and including that as part of your study, I think you're doing a great disservice to yourself and to the scientific community. I think we all need to maybe focus a little bit more on that and at least keep that as a strong component in the back of our minds as we do those studies. So with that, I will conclude. Acknowledgements to the co-authors on this study. It was a very, very fascinating 2-day discussion, and then for a year that followed as we worked the manuscript and answered reviews. The discussions that we had were very in-depth, were very interesting. It was great to work with all of those great scientists. And I thank you for your attention and for your interest, and I will gladly answer any questions.
Thank you, Prof, for the wonderful presentation. Any question from the okay? Question? Can you please come forward, please? Yeah, we have a question for you, Doc.
Sure.
Thank you, Prof. It was nice trying to trigger our interest. But my worry is for a continent like Africa, where this event is holding, how do you bridge the value of death experience that we have? Because when you want to bring Nano to its real world experience, you must involve industries. How do you think we in Africa should be able to bridge this?
So I only heard part of that. Can you say it again?
Sorry?
I only heard part of that. Can you say it again?
Okay, I said for us in Africa, where this event is holding, talking about the sunrise and sunset when it comes to application, real world application of Nano, even as it relates to water treatment per se, the value of death that is seen, that is the gap between the theoretical concepts and the practical applications, ought to be bridged. And one way of doing that is to have a connect between the academia and the industry. So for us in Africa, how do you think we can go about, bridging this gap between the value of death? That's just what I want to know. Thank you.
Yeah, that's a great question. On the one hand, if I had a great answer, I would be very, very rich. Bridging the valley of death is something we've been working for a long, long time. But I think I'll give a couple of potential ways that we can do that. So I think the most important is community engagement and bringing those stakeholders together. Far too often, scientists work in the lab and engineers, are building things, and the engineers aren't asking the scientists what they're learning, and the scientists aren't asking the engineers what they need. And so bringing the groups together can solve problems frequently in ways that neither group envisions. And I'll give one example. So during my graduate studies, I worked on a project with the United Nations in Swaziland, and they had water that they were using for the village to water their crops and for drinking water, and it was very highly contaminated. And so we went to the village and we talked to the people. I went back to the laboratory and I came up with this very elaborate photocatalytic system that would potentially work in the villages. And then when we went back to implement it and we talked to the people, the biggest source of the contamination in their water was the fact that the water was also used as a watering hole for their livestock. And so when the livestock drank from the water, they introduced significant contamination. And the technology solution there, while the reactor that I built would work to clean the water, for much less cost and much greater efficacy, we helped them build a fence around their reservoir, and the water quality improved by 2 orders of magnitude, which is more than my treatment may have done for them at much less cost. And so I think if we don't bring communities together to talk about, okay, where do the real problems lie, we can be working past each other and not having the conversations necessary. When do we need to build a fence, and when do we need to build a treatment system?
Okay, another question. Thank you so much for the question. Yes, thanks for the great talk. Just to say, I'm a professor in fundamental university. My question is, research that has to do with is this an area of priority US Africa? Let's say ARO, in terms of
Yeah, I'm afraid I can't hear you hardly at all.
Is it better or not?
A little. Speak very loudly if you can.
Okay, I'll try my best. Yeah, so my question is, so you mentioned about this drop of enlightenment and illusion and so on. So I wonder, with respect to research in the area of photocatalytic water, let's say for places in Africa, is this still an area of funding priority for the US Army?
Yes, that's a good question. So if I understand correctly, you're asking if this is an area of priority for the US Army. So it is not an area of high priority for the US Army. The application of water treatment is certainly important. I think one of the things that opened my eyes when I moved from grad school research in water treatment to research at an Army research lab in water treatment is that in grad school, I would quote things like the cost of cleaning water per gallon it can cost as little as a few cents per gallon. It can cost as much as a few dollars per gallon. In the Army context, when bringing treated water to the soldiers at the front of a battle requires an armored convoy, the cost is not only dollars, but is also in the lives of soldiers who are sometimes attacked on those convoys. And so to that extent, having the ability to treat water in the field is very important to the Army. Now, that did not always result in large research grants to study different forms of water treatment. Usually that area, because of its connection to environmental studies, may have ebbed and flowed a little bit with different government administrations. if a general says, well, do I need a tank or do I need a bottle of water? Well, I need a tank. And so we always fight that battle a little bit, but the science of water treatment is always of interest, even if it's not always the highest priority within the U.S. Army.
Thank you, Dr. Bray. Any other questions? Other question? I will put our hands together for. Thank you so much. We are very grateful for your presentation. Thank you. For all the participants, we have this few announcements. Okay. We want to announce this. The next section, the technical section, will be coming up by 2. By 2, please. Let's everybody prepare. Yeah, 2 today. Nigeria time. Yeah, 2 p.m. Nigeria time. We have another plenary section by 1:30. 1:30. We have Professor Osama will be presenting by 1:30 plenary section. Then after that one, then we go to the technical section. So we want to make this following announcement, especially those who are here physical. We have section 1, section 2, section 3, and section 4. I want us to indicate, especially those who are here, if you have checked the book of abstracts, you should know where your presentation falls within 1 to 4. Please, for proper arrangements, if you are here, you are in section 1. You want to present physical. Can you please indicate if you are here, section 1? Anybody? Yeah. Section 1 is in the book of abstracts. Check your book of abstracts. Section 1, section 2, section 3, section 4 is in the book of abstracts. Check your book. It's there. It's there. Everything is there in the book. In the program, right? Yeah, check it. It's there. Everything is there in the program. Check it. So if you are in section 1, please indicate. If you are in section 2, indicate so that we can know how to arrange the things. Yeah, we want to actually the value vary in terms of capacity. So we want to know the numbers per section so that we can allocate value for the section. Because we have 2 big rooms and 2 smaller rooms. That's what we want to do. So please check the program, see your section. Hello? We're talking about your home. We're talking about the program. About your home. Please check section 1, section 2, section 3, section 4. Please, if you are in section 1, please section 1, anybody? Section 2, anybody? Section 2, anybody here? Section 3, anybody? Section 3. Section 4, anybody? Okay, we are good to go there. So we're going to have 4 venues. This room is room 1. We have room 2, very close to this place. Yeah, we are going to put the poster there. I'm going to label it room 1, yeah, room 2, room 3, very close to this venue as well. Then room 3, right? Room 4 will be in Zenith building. If your one is section 4, we're going to room 4. If you are in section 4, you go to room 4, it's Zenith building. If your one is section 3, you go to room 3 here. If you are in section 2, you go to room 2, very close here. Then if you are in section 1, you stay here. You stay here in section 1. Thank you. We have a very short break. Then we come back by 1:30 for the last plenary section before we begin the technical section by 2. Yes, sir. Yeah, poster will be tomorrow. It's in the program already. If you check it, you see poster there. Poster will be tomorrow after the technical section. Yeah, today, everything today is all right.
poster is tomorrow at the end of the technical session. Poster. Okay. So please, 1:30, we will listen to the last plenary section. Yes. So please, by 1:30, we'll come back for the last plenary section before we go for the technical session. Thank you. So you can have 30 minutes break. Thank you. Yeah. So, if you look at the sections, so that for the benefit of the participants who are not presenting, section 1 is about energy. So if your area of specialization is in energy, you can join section 1. I think part of section 2 is also energy. Section 2. Okay, section 2, environment. If your area of specialization is in environment, yes, section 3 and 2 is part of environment. Then section 4, X section. X, pharmacy, anything dealing with X, section 4. How does that do? So if you are participating and you are not presenting, you can choose which room to join to enjoy the presentation. Thank you. Yes, Yeah. Please kindly share. Yeah, so you can just so you may check it and just give it a title now. What now, because we are starting the grant session by now. Please,
there that the parallel staging will start by 2. That's why by 2, it's only 2. So before you forward it to now.
Please, ladies and gentlemen, It's for those who registered online. If you paid online, you have filled the Google form. If you have not filled the Google form, please kindly do that now. If you have registered online, we'll pass this across the board. Just cross check your name everywhere and your email before everything is correct. All information will be disseminated through your email. Certificate will be sent to you via your email. So this is very well and make sure that your email is correct. So pass it across now. Check your email. Make sure everything is correct. If it's not correct, accelerate it and give us a message. Thank you.
understand. Okay.
So, okay. The invited guest we are waiting for is not online now. So what we do, Professor Osama Mutanaba is not currently online. So we'll continue the technical section by 2. Please. Yeah, we are going to end this one here now. This is plenary. The technical section will begin by 2. Those in this is room 1. Room 2, once you just step out by your right, you see room 2. Exactly behind the registration desk. Exactly behind the registration desk, you see room 3. You step out from this building, go to the next building, that'll be room 4. Room 4 is for the earth people if you're abstract fall in earth section. So go to room 4. Room 1 here, environments. Room 1, room 2, also environments, some energy. 3, part of environments and energy. Environments, room 3, room 2, energy environments. Room 1, environment and energy for today. So please, you can go to your room. Then please kindly check your name very well. I'm passing the list across. Check your name, make sure that your email is correct. For your certificate and other information. Thank you. Yeah, yes. Hey, you can just record down. You can look to us.